This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. It's a Cosmic Queries grab bag. And you know what that means? Chuck Nice is right here.
That's right.
All right, Chuck.
The fan favorite.
It's a fan favorite.
It is a fan favorite. The people love the grab bag.
Why? And Chuck, we still got Just Smart Enough sitting on our YouTube channel.
That is correct, sir.
That is a all science comedy bit.
Yeah, and it's and guess what? Thank you guys. Everybody's watching it. Getting a lot of great feedback. It's my comedy special. It's on the StarTalk main YouTube channel.
We love it.
Please check it out.
It's pushing through 500,000 views. So
yes, it is.
We're feeling good about it.
Feeling good.
All right.
So this is Sumit Sharma. And Sumit says, while riding my bike, I noticed the dynamo that generates light every time I pedal. I think it converts rotational energy into electricity. In space, things stay in motion. What if we rotate a turbine that keeps rotating forever, generating loads of electricity that we can send back to Earth? Or have big solar fields? Why don't we generate electricity in this way?
So two separate things.
Two separate things.
Three separate things. Let's start with the bicycle.
Okay.
I think what she's probably referring to is one of these devices that leans up against the wheel. So let's go back to the middle 19th century.
Okay.
Michael Faraday.
Yes.
He might be the most important person many people have never heard of because he invented a way to make electricity.
That's right.
All right. He saw a wire and he connected a wire to a little meter. The meter's not doing anything. Took the wire, passed it through a magnetic field.
Yeah.
Didn't just have it sit there. He moved it. And the wire went like that.
Yeah, the meter went. Boop, boop, boop.
He created current in the wire by passing it through a magnetic field. Okay. So, and that was an odd little toy that he made, and he showed it around. So this is charming. And there's a rumored comment where, you know, someone, was it the Parliament, whoever, this is in England. The reply, rumored, was, I don't know of what value this will be to the British Empire, but I know that one day you will tax it.
Faraday was gangster. That is amazing.
Yeah.
That is amazing. What a great statement.
And there's another statement in the same vein, and I don't know if he really said this, but it's attributed. Another one said, well, what good is this? And then he says, of what value to the world is a newborn baby?
Oh.
It's what value will it one day
be?
Well, that's the whole point.
Right.
That's the exact analog.
And that answer could still be nothing.
And that is how all electricity is still made today.
That's right.
All electricity through motion.
Through motion.
Okay.
Yeah.
So
it turns a turbine.
Turbine is wires passing through a magnetic field.
And it creates electricity.
Creates electricity every time.
And I don't care where you are in the world. That's how you get the electricity.
Okay.
That's why windmills.
There's wind turbines.
Right.
There's
steam turbines.
It's the steam that just creates something to spin.
That's all it does.
To go through it. That's what it is. And dams,
where
they let the water go through.
Yep.
It's turning a turbine.
Even geothermal, they use the heat from the earth itself to heat water.
It's not turbines just to warm your home.
No.
Because you can do something with the geothermal.
Well, you could warm your home with geothermal. Nothing else.
Right.
Correct.
But you're not generating electricity.
You're not generating electricity to do so.
Right.
Yeah.
Okay, so now, different from that, you have solar panels.
Right.
Where the energy is already there.
That's called the sun, baby.
Okay. Yeah. You got it.
It's a solar collector.
You have your photovoltaic cells.
Correct.
And that converts the sunlight directly into electricity. And so, yeah, we can do that in space. China has a plan
to put a big ring and do exactly what Sumit is asking to do.
I don't know if it's a ring, but they're going to put up a solar farm in space. So when you're in space, if you're far enough out, then there is no nighttime.
Right.
Because you're not making electricity with sunlight at night.
That's right.
And nor are you making electricity in daytime under clouds.
Correct.
There are no clouds and there's no nighttime if you're far enough out in space. You can always point something to the sun.
24 hours a day.
They would then convert it to microwaves, beam them back down to Earth, to a place that will receive it, and it's free electricity.
And here we are talking about drill, baby, drill.
Still digging oil out of the ground.
Still digging oil out of the ground, and they are talking about putting solar arrays in space.
And we like criticizing them, because they far and away are the largest
coal burning
country. Okay,
in the right.
So it's easy to criticize that, putting a blind eye to what they're actually doing to get ready for the future.
They have coal in China, but they still need more. Okay, they don't have oil, so they need to import that. Guess what you can import, and you're gonna own it outright.
The sun.
The sun.
Okay.
All right, this is Siruns. In Sunshine, you said that if the sun were about to run out of fuel and collapse, any amount of atomic bombs wouldn't matter. But what if we could put giant rockets on Jupiter and throw it into the sun? Would that buy more life for the sun?
I don't know what he's remembering that I said.
Yeah.
Maybe I said it wrong, or he's not
you didn't say
remembering
it
it right.
So what he's trying to talk
the
about
nuclear bomb. Here's what I'm saying. When the sun runs out of hydrogen in its core,
right?
Then the furnace turns off.
Right.
To run out of it means at the place in the sun where it's hot enough to fuse hydrogen, they've run out of hydrogen.
That's it.
Okay?
Right.
All right. Hydrogen is everywhere else in the sun. It's just not hot enough to fuse it.
Exactly.
If you could find a way to stir the contents of the sun, bring outer layers down into the middle,
right,
conveyor belt style, you could feed this nuclear engine with an essentially unlimited amount of hydrogen.
Right.
The amount of hydrogen participating in the sun's generation of energy, I forgot, 1%? I mean, it's tiny. Right. Compared to, the sun is made of hydrogen.
Yes.
90% of the sun, it's to 8% helium, 2% other.
Okay, good. Because I'm like, what?
2% other.
I thought it was just,
yes.
hydrogen and helium.
Yeah, and it's mostly hydrogen and helium. So that would be the way to prolong the life of the sun. In fact, there's star clusters in space, obviously, where they're all born at the same time. And so you expect them to evolve synchronously in a way that the high mass stars die first, the lower mass stars die second. There are some clusters where there's a star that should have died long ago and didn't.
Ooh.
It's called a blue straggler. It was in my time in graduate school where people figured out what that was. You know what it was?
What?
A blue straggler is two stars that collided, stirring up their material, giving
each other new energy.
New energy. That's right.
Oh, that's super cool.
So
super
we
cool.
know the stirring up would work,
right?
Because these stars live longer than they're
supposed to.
They're supposed to. But if you throw Jupiter in, that'll help a little. Okay, yeah. But Jupiter, as big as it is still small compared to the sun. By mass.
By mass, right.
So maybe we should just find another star system.
That's it. All right, here we go. This is David Everett, who says, artificial gravity in movies/TV confuses me. When a starship gets hit by a torpedo, the crew tends to fly out of their seats. If artificial gravity is produced by the ship itself, shouldn't that not happen? And if it does happen, shouldn't the crew get splattered on the back wall when the ship goes into warp or hyperspace?
Okay, two separate questions.
You
get hit with a torpedo.
Right.
So your artificial gravity is creating a force vector mimicking what happens on Earth. And that force vector is always down.
Right.
Let me be precise. That force vector is always towards the center of the Earth.
Right.
For everyone experiencing that anywhere on Earth, it is down.
Right.
Okay?
Right.
Pete Holmes has a gig where he said, the comedian.
Yeah,
Pete
I know
Holmes,
Pete.
He talks about, well, wait a minute. If Earth is in space, then heaven is just away from Earth.
No matter where you go.
No matter where you are. So if you're on one side of the earth, you can say, I'm going to heaven, and point down. Or going to heaven over there. Because for someone on earth, that's up.
That's up.
That's
right.
up.
Yeah.
But anyhow, if I introduce any other force on you, you're going to jolt from that.
Right.
You're going to feel it.
Same way you would on Earth.
You're going to, exactly.
Same way you would.
Yeah, if you're on a bus and then the bus hits a wall or stops, you'll be jolted.
Exactly.
So in space, with your gravity vector doing its thing, if you get jolted, you'll get jolted.
You get jolted.
Okay.
Right.
No, we did an explainer on all the levels of acceleration.
Correct.
It was the jerk.
The jerk.
And we ended with snap, crackle, and pop.
Snap, crackle, and pop. That's what it is.
Dig that up. I'm not going to go over that again. It's all the levels of acceleration that can happen to you.
Yeah, exactly.
So now you want to go to hyperspace. You need some sci-fi hocus pocus.
Right.
to not be splattered on the back wall.
But not warp. You don't need high sci-fi hocus pocus for warp, because that is warping space.
My bad. You are absolutely right. Okay. If you're going to warp space,
right,
that's space doing the work for you. And you just step across.
Right.
You surf it. So that's not a problem.
Right.
So when they show it, the way to show it cool is the thing is there, and then it's off at a thing.
Right.
All right. That'll kill you. Otherwise, you got to find some other way to sort of navigate the space-time continuum in ways that shorten your distance from where you are to the destination.
Right.
So genuine warp drives, if invoked properly, according to manufacturer specs, you should not be a pile of goo.
You shouldn't be a pile of goo.
Yeah,
right.
At the end of the thing.
Very
there's a quick, if I can get morbid for a minute.
Go ahead.
There's a scene in the TV series Expanse.
Oh, I love that.
Where there's a sort of cowboy guy. He's being a cowboy, showing off his girlfriend.
Oh my God!
Showing off
and
he's maneuvering.
Live streaming.
He's live streaming as he's in this craft, and he's maneuvering, and he's badass. Of course, he's strapped in. When you're in one of these things, you're in a 5-point harness, one between your legs, one on each side of your hip, and one across each shoulder. You know what's not harnessed?
Your head.
That's how Dale Earnhardt died.
Yeah.
Okay? He hit an embankment. His head is not restrained. The head keeps going.
Snaps,
at 160 miles an hour.
Right.
And the body stays there because it's strapped in.
Yeah.
Okay?
They're all chained in now.
Yeah, they are. Yeah, they have a connection to the back.
To the tether.
He had that option at the time.
Oh, damn.
But
he's probably too old school for that.
Old school. You're not going to do it. So in the scene in The Expanse, he goes through a membrane.
Right.
Where his spacecraft stops. He's stopped at the membrane, but he doesn't.
Yeah.
And it's pretty graphic. It's a pretty graphic.
But it's kind of cool.
And they would later say, here's why the craft didn't crumble, because he was going really fast.
Yeah.
And then stopped on an instant. Yeah. On a dime.
Yeah.
All right.
Wow, that's pretty cool. All right. Very cool. This is Dave Hartman. He says, hey, where's the gravity particle? Everything else has a particle of some sort. What's the deal with gravity?
We're looking for it, okay? Give us a chance here.
Right.
But the energy of the graviton is really low, and we don't know how to go that low.
Right.
Okay?
Yeah.
That's the problem.
Because gravity is like a super weak force.
It is the weakest force in the universe.
Right.
You know, when you want evidence of that?
Yeah.
Bend down and pick up a rock. Okay? The entire Earth was insufficient to prevent you from picking up the rock.
Right.
Think about that.
Because, the gravity didn't change.
Okay.
That rock is on the ground because of gravity.
Do you know what is 42 magnitudes, powers of 10 stronger than gravity? Electromagnetism.
Oh, my God.
42 powers of 10.
That's incredible.
Which is why you go to one of these magnet doors, you can't open it.
Right. It's true.
It's just two plates of,
Or when you get electrocuted, they can't pry you from the wire.
What? Why'd you get dark?
I'm sorry. I don't know what my problem is.
No, but the doors that are magnetic, the doors that are magnetically locked.
Yeah.
And when you push a button,
and they unlock.
It's an electromagnet,
right?
And they just unlock.
Yeah, and you cannot open those doors.
Okay, maybe if you tried really hard, you risk breaking the door. And that's just the circuitry in the thing itself. And you have all of Earth trying to hold on to the rock. And you thwart it.
And all you do is come by just like, look at you, little girly Earth. Here we go.
We presume there's a graviton particle corresponding to gravitational waves, just as there are photon is a particle corresponding with waves of light. Yes,
and the electron.
Yes, okay,
for the electromagnetic.
Right. So all of that combined.
Yeah.
So we're looking for it. Just chill.
Yeah. All right, here we go. Michael De La Morena. Is time a dimension or a field? It seems more like a field because it can be affected by gravity.
I like that. I don't know that I have a good answer for that. The idea that gravity can distort time.
Correct.
In the way, the way things interact in fundamental physics. There are fields that affect particles that affect fields. So that's an intriguing thought. and I might bring that up with
Brian Greene.
Yeah, we scheduled a session for him, and where we're going to pick his brain for 3 hours.
Yeah, it's going to be a long session. I'm going to smoke weed that day. All right. It's a good.
We're going to poke his brain. I don't know how much brain will be left by the time, but we're going to get all in it.
Yeah.
It's an interesting concept.
It's a really good concept.
Yeah. But for now, we think of it as a dimension in which we are trapped in the present.
Mm-hmm. Mm-hmm.
And you know the rest of my quote there?
Go ahead.
We are prisoners of the present.
Yes.
Forever transitioning between our inaccessible past and our unknowable future.
It's a really great quote. It's really good.
I'm just saying.
No, it's great.
We're kind of stuck.
Yeah.
But you're not stuck in space.
Right.
You can move this way or this way.
Space any way you want.
Jump up and down.
Right. Any way you want.
So one day, if we can conquer time, we'll have access to our entire timeline.
Right. I only want to see parts of my timeline. I'm going to tell you the truth. All right, this is Textile Wiz. He says, hypothetical, Neil. You're given 40 yards of 0.15 millimeter steel wire on a reel with no markings.
Mm-hmm.
Would you use it as fishing line or listen to the 1 minute message it may contain? How could you possibly know it contained information?
Why would there be information in the wire? Why is that even a thought? Okay, by the way, if every part of the wire is identical to every other part, it cannot contain information.
Why not?
Because information is this configuration of whatever you have is different from this configuration, is different from that configuration. Right. And the information is contained in the difference in these configurations.
Mm-hmm.
That's where you get information.
That's where you get information.
If it's identical,
right, there can be no information because it's all the same all the way through.
It's all the same all the way through. Or the only information it's giving you is what's the orientation of the atoms that give you the string.
Correct. Yeah.
Okay.
Right.
And often that repeats.
Yes.
Typically,
and it normally is.
Like in a crystal, the patterns repeat.
Right.
So you only have information enough worthy of one of these patterns because once it repeats, it's not more information.
It's not more information. It's right. It's just a repetition.
So Chuck, that's the difference between having 2 newspapers and 2 oranges.
Aha.
Okay.
Right.
2 oranges, you got 2 oranges.
You got 2 oranges.
2 newspapers, you don't have twice as much information.
Right. You just got 2 newspapers.
You just have 2.
But they got the same information.
The same information.
Gotcha.
Okay.
Right.
Yeah. So I don't know how information would be embedded in the wire. I'd have to know that in advance to even attempt that.
Right.
But clearly that's what I would do if I had any suspicion.
If you had any suspicion. So the answer is go fishing. No, that's not the answer.
But it's a steel wire.
It's a steel wire.
That's a big fish.
I don't know what you're catching. We
Yeah.
catching some tuna, some sailfish.
What's the difference between a sailfish and a sunfish?
Oh, the sunfish are the big giant fish with the funny looking heads.
What's the one with the
and
thing?
That's the sailfish.
So what's the sunfish?
The sunfish is the big, like fat, like it's just got a big, fat, long head.
Okay.
That's the sunfish.
I'm just a city kid.
And little teeny. All right.
Okay.
All right, here we go. Stephen R. Small says this. Assuming spiral galaxies are evenly distributed, I'd predict an even split of spirals turning counterclockwise versus clockwise, plus a small fraction on edge where spin can't be detected. What would be learned if that prediction were true or not? And putting aside expansion of space, is a galaxy's translational travel vector aligned with its equatorial plane like a frisbee?
For the longest time, people have wanting to use these massive data sets of galaxies in the universe to see if there's an orientation of the spiral galaxies.
Right.
One way or another.
Right.
Because they're going to spin.
Yeah, they could spin.
That way.
Right. And they can spin edge on, flat,
right.
All kinds.
And who is this that asked the question?
This is Stephen R. Small.
So Stephen presumes that if it's edge on, you wouldn't know which way it's spinning, but we do.
Oh.
Yes, you can put a slit across it and get its spectrum, and you'll see that one side of the galaxy is blue shifting towards you, and the other side is red shifting away.
That is brilliant.
Yeah, yes. My people are brilliant.
I love that.
My people are brilliant.
That is so cool. But go ahead.
Yeah. So you know if it's coming towards you, even though it's edge on.
Right, even though it's edge on.
Yeah, okay.
You can see what's blue shifted, what's red shifted, the other. Oh.
So another fact I must correct is if you randomly scatter spiral galaxies into any environment, the most likely way you will find them is edge on. So here's the dish that's the galaxy.
Okay.
Okay. Here's a face-on galaxy.
Mm-hmm.
So let's say the North Pole is pointing to your head. All right. That's also face-on.
Correct.
The North Pole is pointing that way.
Mm-hmm.
To get a face-on galaxy, the galaxy has to be facing you to be a face-on galaxy.
Right.
Or it could be the other way.
The other way.
So there are only two ways
Right.
the pole can be pointing if you get a face-on galaxy.
Exactly.
Okay? Edge on, oh my gosh.
Oh, you can go in all the way around the clock.
At edge on, the pole
Anywhere you
can
want to
be
go.
an entire circle
Right.
this way, and you are edge on the entire
The whole
way.
thing.
There are more ways to configure edge on galaxies than face-on galaxies.
Okay.
In a random set of galaxies.
Absolutely.
Okay.
Yeah,
and you can show that probabilistically and statistically. And
Cool.
it's an exercise in graduate school. You do this. So don't be surprised when you look at the Hubble Deep Field and other things. There's a whole lot of edge-on galaxies.
Right.
Okay.
Right.
People have been looking for extra rotating one way versus another. And the first time someone made that claim, they had room full of people saying, which way is the galaxy rotating? Just they ignored the edge-ons. So which way is the galaxy rotating? And people made their catalog. They said, oh my gosh, there's a net rotation clockwise. Holy cow, what's going on? And then theorists started coming in. Maybe there's leftover rotation from the Big Bang. And people started jumping all in. I call them ambulance chasing theorists.
That's funny.
All right.
Go ahead.
So then someone had the idea, let's give this same test to a different set of people, except have them look at the photos from the other side, the mirror image of the photo.
Image, okay.
They evaluated the thousands and thousands of galaxies. Once again, most of them were rotating clockwise.
Right.
That's not possible. I just flipped them all on you.
Right. That's a mirror image.
Right. So they concluded that there's a psychological preference for noticing.
So we have a bias.
We have a visual bias.
We have a bias that allows us to look for that.
That's right. And so we said, we're not going to have humans doing this ever again.
Right.
And so we train computers. AI is coming in at the time.
Course, right.
And someone now has a section of space, not the whole, all of sky, a section of space where there's a net angular momentum a net spin in one direction and not another. And that's in the last year or so.
Okay.
So check that out. And we think it's not going to hold up, but it's nonetheless an observed result that people are contending with. Yeah.
Well, Stephen, way to go, man.
And we're using spiral galaxies because elliptical galaxies don't have the stars are like beehive.
They're doing all kinds of crazy crap.
Right. It's not really
Whereas the spiral galaxies are uniform.
It's a uniform rotating system.
Yeah. Mm-hmm. Which by the way, we're in one.
We're in one. We got one.
There you go. All right. This is Jose Ikamba. Jose Ikamba, who says,
by the way, is there an accent over the E?
Yes. Jose says, in Fantastic Four, First Steps.
I remember the day that movie premiered. It was highly advertised. It looked intriguing, looked even fun. Haven't seen it yet.
Still haven't. Me either. He says, Reed Richards considers teleporting Earth into another universe to save it. Realistically, with current technology, what could humans do to move Earth from its orbit around the sun, analogous to DART or Dimorphos, but on a planetary scale? How plausible is it?
You got to really understand how much mass there is on Earth.
Tell me about it.
Okay. I did a calculation. Do you know they bench test rockets?
Okay.
Space rockets.
Okay.
In the desert. So you know how they do that? They could point them upwards and see how far they go, but they don't. They anchor them to Earth, ignite them, and measure all the forces and the pressures and the temperatures and everything. I thought to myself, if they kept doing that,
we could increase the rotation of the Earth.
I said, are they slowing Earth down? Because if it's perpendicular to our rotation, that would have a different effect. It wouldn't speed us up or slow us down. Right. But if it's due east or due west, oh my gosh. So I ran the calculation.
Not going to happen. Huh?
It's not going to happen. It's nothing.
Right.
Compared to the rotational inertia of the Earth. So
it's a mosquito punching an elephant.
Not even.
Not even a gnat.
It's a gnat. Yeah. So it's not a thing. So, but as I said, in other recordings we've made, there's a movie made in China, but with an international cast called Wandering Earth 2.
Okay.
I never saw Wandering Earth 1.
I haven't seen either.
Okay, but Wandering Earth 2, there's something wrong with the sun. They got to take Earth somewhere else. There's no teleporting. It's kind of in present day, actually. Maybe a little bit in the future where they have space elevators and things, but it's not it's not Star Trek future.
No.
All right? They got regular rockets. So they said, we got to move Earth. And they set up these rockets around the perimeter of the Earth, all pointing the same way. And then they ignite them all. And then Earth slowly pulls out of orbit to another star system to enter ourselves into their orbit.
Wow.
Now then you could choose where to put the orbit.
That's true.
Get the right exact
Get the
temperature.
exact temperature, everything you want. And wait, and the closest place we could go, which is not even a real star though, right? Isn't that Proxima?
No. Alpha Centauri is a system. Proxima Centauri is the closest star within the Alpha Centauri system.
That's what I'm saying. So we would
Hence
have to go
the name
to
Proxima.
We would have to go to Proxima because that's the closest we would.
Yeah, for every star, there is a distance that would be the right Goldilocks distance.
Right.
So we can pick any star in principle and just go
and
to
just
the
go
spot.
to that spot.
Yeah.
Okay.
Yep.
All right. So this is Tam Tam. Hey, Tam Tam. In relational physics.
This is very like psychotherapy.
This is, when different observers describe the same process differently, what is considered invariant? What actually holds across those perspectives?
I like that.
Wow.
You know what's invariant? That's a great point. Because two people seeing the same thing, interpreting it differently. Is there anything that's constant?
Right.
Yes. The speed of light.
Ah, look at that.
So no matter what's going on, if they measure the speed of light, they're going to get the same answer.
Oh, look at that.
Now, there are other invariants. That's the simplest one I could describe. There's others where there's a combination of your light, your travel in time and your travel in space. And so the length of that vector is the same for all the observers, if I'm remembering this correctly. I'm going to check with Brian Greene again on this. But the combination of those two is invariant. So for me, my space vector might be longer than my time vector relative to you. You can have a longer time vector relative to space vector. But to connect the two ends, that length would be the same. And that would be the same throughout the system.
Interesting.
I think I'm getting that right.
I got
It's been a while since I dug into it.
Right.
But you see what I'm saying? And so just look at a triangle.
Yes.
And the hypotenuse of the triangle would be an invariant. But the triangle that gives you that hypotenuse can have varying the legs can be a different size relative to each other. Exactly. And these two legs, one is time and one is space.
Oh, okay.
Yeah.
All right. Now that's a very good way to explain it.
Yeah.
Does that make sense?
If that works out. Yeah.
Okay. Wow. Tam Tam.
That's a good deep question. And so invariants are the things that would be constant, and you want to know what those are because those are mathematical jump points from one observational system into another.
Wow. Look at these people.
I know. We got some good people.
Diana Smith says, how can galaxies collide if everything is moving away?
Oh, I love that.
More precisely, how is it that while the universe is expanding and moving away from us, the Milky Way and Andromeda will collide in the near future?
Okay, you ready for this? You ready? Okay.
Go ahead.
So galaxies that are near each other feel each other's gravity.
Right.
And they have speeds in response to that gravity. All right. So I'm going to pick a number. Let's say 200 miles per second.
All right.
Okay. Let's just say, so that's a characteristic that goes much higher in galaxy clusters. Let's just say, picking a number, 200 miles per second. These galaxies feel each other and they're moving around each other. The universe is expanding. Well, the bigger is the distance between two objects, the faster it's expanding. If I'm not far away enough from this system for the expanding universe to be greater than 200 miles per second, the expanding universe will not manifest in this system.
Right.
If I go far enough away so that the universe is expanding 400 miles per second, it's going to rip these galaxies apart.
Exactly.
So galaxies nearby each other are not spread over enough space in the universe for the expansion of the universe to manifest.
Oh, gotcha.
However,
Uh-oh.
in the Big Rip,
Okay.
The accelerating universe,
Yes.
there's a point where the expansion of the universe will rival the relative speeds of galaxies that are near one another, and it'll rip them apart. And then it'll rival the speeds within the scale of the galaxies themselves, and it'll rip the stars apart. Then it'll rip the planets off the stars. Then it'll rip the atoms out of the star. Then it'll break the atoms apart. Then it'll break the electrons off the atoms. Then it'll break the nucleus apart.
And that is because the acceleration is constantly increasing.
Constantly increasing.
Right.
And it'll outstrip
It
anything.
outstrips anything.
Anything that would otherwise be holding itself together.
You can't outrun it.
Can't outrun it.
Can't outrun
That's
it.
a good way to say it.
Yeah.
So that's why only nearby galaxies will ever show a blue shift.
Oh, look at that.
Yeah.
That's very cool.
Yeah.
Good
And
stuff.
it's only when the red shift outmuscles it.
Right.
And so no faraway galaxy has a blue shift.
Has a blue shift.
Nope.
These people are very smart.
And we are on a collision course with Andromeda.
Andromeda, right? Because we're close enough.
Yeah, in like 7 billion years, plus
there
or
you go.
minus.
Yeah, so stick around, Diana.
October 3rd. It's been 7 billion years.
All right. Bill says, in the classic depiction of a supermassive black hole, e.g. interstellar, the accretion disk looks aligned flat, horizontally from our point of view. Does a black hole look the same from all sides, left, right, top, bottom? Doesn't make a difference. And is it even possible to get behind a black hole?
Yeah, so I'm impressed that he called that a classic description.
Right.
That's only been with us for like 10 years or so.
Right.
Ever since we've had enough modeling, enough physics, enough theoretical understandings. So I'm impressed that that's now classic.
That's classic now. That's funny.
And it looked like you were coming in on the accretion disk, but there's distortions in the space-time continuum in the vicinity of the black hole. So that the accretion disk behind the black hole has sight lines that come around the black hole to you, bending the light around.
That's amazing.
So you're seeing this sort of unfolded image of a black hole in all places.
You see behind it when you're in front of it.
So you can go behind the black hole,
Right.
but then I'm going to see your ass in front of the black
That's
hole.
right.
Because the light travels to it. And when you see curved light, you don't know that it's curved.
Right.
As far as you're concerned, it's a straight line. Just like when you see the sunrise,
Right.
the sun isn't there.
Yeah.
The sun is 5 minutes below.
Right.
Because the light refracted, it's not for the same reasons, but I'm saying if the light bends and you see it, you don't see bent light.
Right.
You're
seeing the light.
You're seeing a straight
Straight
line. What
line.
you think is a straight line.
Because that's why you see it.
That's where you see it. And it's the refraction of the atmosphere that 5 minutes later the sun actually rises, but the atmosphere bent it into your view and you think it's in a straight line.
Woo!
So
That's so cool.
That's what's going on
That's
there.
what's going on in the black
You can see
hole.
all sides of the thing.
That's dope.
Totally dope.
That is amazing. I love it.
I answered that quick, didn't I?
Yeah, you did.
Whoa.
Yeah.
Absolutely. I answered that quickly.
Yes, you did. Thank you for doing that. This is Dalton. Greetings from Huntsville, Alabama. I was watching an old explainer on absolute zero and why it's impossible to reach it. If
Nice.
it is impossible by quantum physics to have a particle become completely stationary, then would it not be possible to extract infinite energy from it in the form of heat? In doing so, violating the first and second laws of thermodynamics. It seems a bit paradoxical to never be able to reach absolute zero, since you seemingly can always have something colder. But that, I don't know why you would say you seemingly could have something colder.
No, he's what this is, Dalton. He's merging a classical brain with a quantum brain. Okay.
Right.
In terms of his interest in answering the question.
Right.
So just let me talk you through this.
All right.
So let me just remind people that there's no such thing as cold.
Right.
You can't like put cold in something.
That's where I was going when I said it's...
If you could do that,
right,
then you can make something like infinitely cold.
Yes.
Just add more cold.
Add more cold.
So what we sense as cold is just the absence of heat.
Right.
So you start pulling heat out.
Right.
This is what your refrigerator does.
Right.
It pulls heat out of your food.
Right.
We don't think of it that way.
Right.
You put in something that's room temperature, it takes the heat out.
Right.
If you take heat out of something, what happens to its temperature?
It goes down.
And you take it out, where does that heat go?
It's got to go somewhere.
It's got to go somewhere.
Sure.
You ever go around back of a refrigerator?
Goes out the back of your refrigerator.
You ever go around
It's
back?
hot as hell back there.
You ever go around back?
Yeah, it's
Those coils are dissipating coils to send out the heat.
Send out the heat.
It not only radiates the heat, but it's in touch with air,
Right.
so the air will conduct heat away as well.
Right.
Okay? By the way, this is a major issue with spacecraft.
Okay.
Because if you're in space and you have machines that generate heat,
Right.
how do you get rid of the heat? You got to dump the heat somehow.
Okay.
So you can't just have, well, you can have radiators, yes, but each radiator has to be pointing away into space. They can't point to each other. You can't have a battery of radiators, right? Not a literal battery, but like
an array, an alignment.
An array of radiators that are like, if they point to each other, nothing, it just feeds each other the same heat.
It's like, I'll heat you, you heat me.
Exactly. So they all have to face space, but it doesn't have the benefit of air whisking away the heat. It can only radiate it away. Whereas on Earth, you can release heat both ways.
Okay.
It can radiate away, and you can convect air around it, and it just takes it away.
Right.
Very efficient.
Right.
When you have a medium such as an atmosphere to do that. Right. All right. So
cool breeze.
The cool breeze will cool you down faster than just you radiating your whole heat. Okay.
Right.
It's slightly different. The cool breeze is forcing your sweat to evaporate.
Right.
And the evaporation takes energy out of you. But so let's get back to the absolute zero. So I keep taking heat out, and the temperature gets lower and lower and lower. You reach a point where quantum phenomena dominates, and you can no longer use classical reasoning. This, by the way, Dalton's not alone in this intersection, this troubled, paradoxical intersection between classical physics and what we call modern physics.
Okay.
So you get down there, and you try to take more heat out, and you can't because and by the way, taking heat out means that particles are moving slower and slower.
Right.
Okay. The heat is vibrational energy typically. Okay. So you take that out, and there's a regime where the quantum fluctuations prevent it from ever stopping its motion. All right.
Okay.
So you're saying, that means there's energy there.
Right.
Let me pull that energy out.
Let me utilize that energy.
I think I'd have to confirm this with our cosmology trio.
Brian and Jana.
Brian Cox, Brian Green, and Brian Cox, of course, is in the UK.
Right.
But he comes through, and he's a good friend.
And then sometimes Sean.
Sean Carroll.
Right.
Oh, yeah, he's a good guy, too. When we speak of 0-point energy of the vacuum of space,
right,
I think that's what they're referring to. The energy below which you cannot go,
okay,
because it's 0 point, but it's not really zero.
Right.
But if you try to get to zero, that's what you're stuck with, and that's quantum fluctuations. And I don't think you can extract energy out of that lowest energy fluctuation, because it needs to take energy out. You need a lower energy state to land
on, right?
And you can't,
right? Because that's it.
Who's that guest we had in another show? A biologist who said the universe is just electrons looking for a place to rest.
That's it. Yeah, that was Bitul.
Bitul. Yes, Bitul from University of Madison, Wisconsin.
Yes.
Bitul. The universe, everything that happens in the universe is an electron
looking for a place to rest.
Looking to hang its hat.
Yeah.
So, but people imagine that you could tap this 0-point energy and make like rockets out of it and travel through space. And I don't have problems people imagining that. It doesn't seem likely to me, though, based on what we know of the behavior of quantum physics.
Gotcha.
So there you have it.
All right, Dalton, way to go, brother. Hope that keeps you from,
keep you on the ledge.
From jumping off the ledge. All right, this is Rachel Ambrose. Rachel says, Rachel here from Austin, Texas. Photons have to be literally everywhere all the time, even in a dark room. If I can see, then there's photons hitting my eyeballs. I feel like people don't talk about this enough. They are filling every inch of space all the time. They're everywhere. Furthermore, somehow photons from the Big Bang are still here right now in the form of cosmic microwave background radiation.
Muhammad Ali said it best. He knows that photons have to go,
Right.
Well, he's thinking that dark is penetrating the room, but light is exiting the room when you turn off the light. The light gets absorbed and it's gone. Your eyes are not the ultimate arbiter of whether there are photons in the room.
Right.
Because your eyes only see red, orange, yellow, green, blue, violet.
Roy G. Biv.
Yeah, sorry, indigo, violet.
Indigo, violet.
If you got to get the Biv going there.
Yeah.
Isaac Newton put in the eye.
Did he?
Yeah. Because he's mystically fascinated by the number 7. The spectrum can't have 6 colors.
Can't have 6 colors.
You got to.
Yeah.
No, but if he got deeply religious, he could say, well, the universe was created in 6 days.
Right.
You know,
there you go.
It's not 7 days, 6 days.
Yeah, that's
people
what
forget. It was 6 days.
6 days. 7th day he rested.
He rested.
Which I'm just saying, what kind of God is this?
So anything that is at any temperature at all
Right.
is radiating photons.
There you go. That's what I was going to say. Because if you're a predator, you see photons all the time.
You mean the movie character?
Yeah, the monster with the dreadlocks.
Yeah, he had dreads.
Yeah.
He had dreadlocks.
Yeah.
So Predator
I didn't appreciate that.
could see in infrared.
Right.
Okay.
Exactly.
Now, you know what's interesting?
Go ahead.
Just a little fact.
Right.
'Cause I think about movies all the time.
Okay.
So that was only cool because the infrared was the shadowy shape.
Right.
That means he has low resolution infrared cameras.
Right. Yeah.
We got better cameras than that today.
We do.
High resolution, you see the full person there. Depending on your temperature,
Right.
it will determine what kind of light you're predominantly going to emit.
Right.
So at our temperature, we emit primarily infrared, so we'll show up in infrared. We reflect visible light,
Right.
but we emit
infrared.
Your walls are room temperature, so they'll emit a little less infrared because they're not as warm as we are.
All right.
You keep dropping the temperature. What's on the other side of infrared? Microwaves.
Okay.
And then radio waves. So the colder it is, the further down the spectrum it shifts. So that when you're only 3 degrees Kelvin, 3 degrees above absolute, you're giving off microwaves.
That's it.
And that's the cosmic microwave background.
Space, right.
That's it.
Cosmic microwave
Cosmic
background.
So yeah, and it could be dark for you, no problem. Not many people have been in complete, total darkness in their life.
True.
Do you know how to get it?
I'm going to say blindfold and
that can help.
and then bury yourself alive.
Okay. I was thinking of other ways for that.
Okay.
But if you go spelunking.
Oh, you mean to a cave?
Into a cave. You go deep into a cave, make a few turns.
So there's no light getting in at all.
Turn off your flashlight.
Right.
You cannot see
anything.
Anything.
Yeah. This is Max Wilburn who says, "Hey, Chuck. Hey, Neil. This is Maxwell from Lexington, Kentucky.
Ooh.
And I know Neil thinks very highly of Newton as he has accomplished so much. But recently I learned about Newton's law of cooling. Although it's not as fundamental and such a stepping stone for the world of physics, I just find it insane that as a side quest, he did that. What a badass.
So I didn't know he came up with that, but it is a well-known means of calculating the rate of temperature change in physics class.
Okay.
Yeah. So the way you do it is you have two materials at different temperatures.
All right.
Okay. And you bring them in contact in some way, either physically, so that atoms are touching each other, or have air molecules bouncing back and forth, or they're radiatively connected. You connect them in some way.
Okay.
Okay. And then you measure the rate at which the temperature changes so that they reach equilibrium to each other.
Cool.
Okay.
Right.
So it's not just that sorry. One of them might have a continual source of energy going in. Mm-hmm. So then the cool thing comes up to its temperature. You see what I'm saying? But if they're two isolated objects at different temperatures, they will meet in the middle somewhere.
Right.
At a temperature lower than the high one and higher than the low one.
Gotcha.
All right. So you can calculate the rate at which the temperature changes.
Oh, okay.
Okay? And deduce, as Isaac Newton apparently did. I own everything that man's ever written, and I've got to go dig that up.
You got to go dig up the law of cooling.
That must be a chapter I missed.
Yeah.
Okay? So what it states is the bigger the temperature difference, the faster the rate of change of temperature will be.
Okay.
Which kind of makes sense. It just kind of makes sense.
Yeah, absolutely.
Yes.
Right.
And if you do some measurements of that, you can actually represent it with an equation.
Okay.
And you make a prediction.
Right.
This is the temperature difference. They'll be the same temperature in 10 minutes.
Right.
Or, by the way, this is happening every day. You get a glass of water, you put ice in it.
Right.
Eventually,
it's going to be water.
The ice will melt. And then you have water that's cold, but it's still air temperature out here.
That's right.
Eventually that comes up.
And that comes up. That was an assignment in physics class when I was in 8th grade. And what we had to do was plot the melting of the ice in a graph to see whether or not it was linear. And it was.
Yeah, that would be a cooling curve.
Yeah, that's a cooling curve.
It's gaining heat from the outside.
Exactly.
Yeah. He never married, had no children, had no known intimate relationships. And so we're pretty sure when he came up with his law of gravitation and motion and calculus,
right,
that he was a virgin.
Right. There you go, babe. That's it. Ben Grun says, "Hey, StarTalk. This is God, here to bestow upon you the keys of limitless energy.
Ooh.
What do you do?"
Oh. Wow. Well, first, I don't think it requires God. We just have to tap the energy from the sun.
There you go.
We're kind of slow on the go here, but the sun has basically unlimited energy. And the Chinese now want to put up a solar array in orbit, where there's no clouds. And if it's far enough away from Earth, it always sees the sun 24/7, beam it down to Earth by microwaves. So then you have this column of microwaves. But unlimited energy. Yeah. Here's what I would do. You ready?
Go ahead.
I would do what they did in Iceland.
What's that?
Iceland is sitting on top of volcanoes. You know this?
Yeah.
Okay. So it's volcano land. It's not Iceland.
It's not Iceland, yeah.
Greenland is Iceland, not Greenland.
Right, exactly.
All right, it's the opposite here. So I want to do what they do in Iceland.
Go ahead.
They heat their water at these lava pits up in the mountains and then send the water into town, but they do it under the streets so that snow never accumulates.
Genius.
You don't need snow plows. Right. You don't need salt.
Right.
You don't need accident reports.
Nope. It snows and then the streets are they're just clear.
I would run hot water under everything. And then you just snow be damned. It's
radiant heating for your whole city.
Yes.
Wow, that's cool.
Yes, and other things I might use unlimited energy for.
I'll tell you what I'd use it for.
What?
Pretty much shutting down every war that's ever been fought. Because most of these wars that we fight are over some form of energy,
right.
And so it's just like, well, guess what? It's unlimited, guys. What are you fighting over?
Well, it could also be over food,
right.
or water supplies. There are other causes.
There are other scarcity resources.
Right. But I think we'd be smart enough.
But with unlimited energy, you would make water.
Today, nobody is going hungry because there's not enough food in the world.
Exactly.
If you're going hungry, it's because
some greedy bastard is keeping you from getting food.
Disrupting the food chain.
Exactly.
So I don't think that was predicted back in 1900.
No, right.
We saw the population growing exponentially. And we saw the food supplies growing linearly.
Yes.
And
there was a point where people thought that we would run out of food.
And just completely starve.
Right.
And so run out of food to feed everyone.
Right.
Rich
people always going to eat now.
Right.
Exactly. Yeah.
Yeah.
Wow. So that's cool, man. I love the idea of radiant heating for your city, though.
Yeah, just for this, just so you don't have to do it.
Yeah, especially since we got 2 feet of snow. All right, I love that answer. All right. By the way, I think this is why Trump wants Greenland.
What?
Because he really thinks he wants Iceland. All right, this is Scott Oppenlander, not Open, Oppenlander. And he says, "Hey, Neil. Hey, Lord Nice. Scott Oppenlander here, tuning in from Phoenix, Arizona."
Which I'm told is a quarter mile from the surface of the sun.
Anyway, since our universe appears to be a pancake shape, like planetary systems and galaxies, do galaxies orbit around some larger central structure, like an even more super mega massive black hole? Or are galaxy motions just more random or ununiformed? There you go.
Universe is not pancake shaped. So next question. No, but to the point, galaxy motions are mostly random. And what I mean by random is they're not coordinated in some big way unless you're part of a galaxy cluster.
Okay.
And then there's some ballet of movement. However, some structures in the universe are so large that the average speed of the galaxy moving among other galaxies in that cluster is insufficient for the galaxy to have made one complete loop through that cluster.
Okay.
So that has significant consequences to what's going on there. It's not virialized. A virialized cluster is a cluster that has a very mature shape, where, like a beehive, all the galaxies are moving around. You step back, it has a spherical kind of envelope that contains them.
Gotcha.
But if it's kind of ratty, like that, it's not yet virialized. It comes from what's called the virial theorem, which talks about how energy can be transmitted, shared from objects with high energy to objects with lower energy, so that everybody has approximately the same energy at the end of the process.
Very cool.
So virialization is the sharing of that energy.
Sharing of the energy.
So it drops the energy of the high energy objects. It could be thermal energy. It could just be orbital energy, and the lower energies come up. So, but it's a whole branch of physics. We talk about virialization of
galaxies,
of matter in
matter
whatever situation.
Okay.
So the ratty-looking galaxy clusters tend to not have been virialized.
Gotcha.
And so, yeah.
All right. So,
and by the way, moving around the center of our galaxy takes about 200 million years.
200 million years.
That's much smaller than the age of the galaxy, which is 13 billion.
13 billion years, right.
Yeah, so galaxy is a mature shape.
And we're in a spiral galaxy.
Correct,
so
correct.
That's very cool, man. Good question. This is MX self-destruct. Okay. MX,
is that a
that's what it says
is that
here.
a thing here? Okay.
MX self-destruct, I have no idea. But his name is Seamus, and he says...
Seamus?
Yeah, he says, Dr. Tyson, Lord Nice, Seamus here from Los Angeles. We know that gravity is the result of the way space-time curves. So wouldn't it be more likely that gravity is simply a side effect of this curvature rather than a force with a carrier particle like a strong, weak, or an electromagnetic force? If there is a carrier particle, why is it not just the Higgs boson, since that imparts mass, thus providing the curvature for the universe that we call gravity?
Wow, people
are doing some work, man.
People
are doing some thinking,
man. So I can answer 80% of that question.
All right.
It's an assumption that gravitation, as a force in the universe, has a force carrying particle.
Right.
And the assumption is that if you represented classical gravity, even Einsteinian gravity, with quantum physics, it would have to have a particle. So we even named this hypothetical particle.
Okay. The graviton.
The graviton.
Right.
Exactly. So the hunt for the graviton is on.
Right.
All right. And so the effect of the graviton and mass and energy is to curve the fabric of space and time, forcing you to move in certain ways that would not otherwise be the case if that were not occupying that space.
Right.
John Archibald Wheeler, a great physicist of the 20th century. In fact, I had him as a professor in graduate school.
Wow.
Okay. In fact, I met my wife in relativity class that he was teaching.
Cool.
I was sitting in the back row. She was in the front row.
And then you guys made relatives.
What I can't quite wrap my head around is if gravity is just the curvature of space and time, maybe it's not a force.
Okay.
Because forces have these carrier particles.
Right.
And if you're just falling along a curvature of space and time, what does it even mean to think of that as a force?
As a force. Right.
Right. So maybe it sits outside of the quantum paradigms that would require that there be a graviton.
Boy, that's kind of cool, man, in a way, because that means that there would be something in between the quantum.
An understanding that we don't yet have.
An understanding we don't have.
Right. It's a frontier.
Yeah, that's cool.
For sure. All right.
Well, there you go, buddy. I mean, listen. Now, you did some good. That's a great question. This is John Mayer. I think it's Meyer or Meyer. He says M-E-I-E-R. Meyer.
Yeah.
John Meyer. Salutations from John in Carlsbad, California.
Carlsbad, California.
Yeah, Carlsbad, California. He says, Dr. Tyson, Lord Nice, the great defenders of art curiosity. I have a question that has plagued me. Plagued
that's
my
a
mind
T-shirt if there ever was one.
Yeah, the great
StarTalk, the defenders of curiosity.
He says, as budgets seem to be one of the significant components of innovation in science.
Yes. It's not a component of whether or not something is found to be true. It's a component of whether or not the research is conducted at all.
Exactly. He says, if we were to greatly increase the national or hypothetically the global science budget for building telescopes, what would you propose to maximize mankind's current technological possibilities, and what could they deliver in order to create the most powerful telescope possible? What would it look like? What would you point it at, and what might we see?
Oh, I would put an entire array of telescopes on the far side of the moon.
Right.
There's no atmosphere, so there's no clouds or anything. So there's no value to being on a mountaintop. You don't even have there's no value to being in an orbit.
Right.
The whole point of the orbit is you're outside the atmosphere.
Exactly.
On the moon, there's no atmosphere. You're good. You're good to go. So I put them all on the far side of the moon. And it doesn't even have to look towards Earth, where we have all of this contaminating radio wave noise and everything. I mean, Earth is just this messy thing in space.
It's terrible. That's a great idea, though. Put it on the far side of the moon, though, to watch. Put all the telescopes there.
Yeah, and then you put of all bandwidths.
Right.
You put all the telescopes of all the windows of the electromagnetic spectrum.
Right.
The radio waves.
Yeah, everything.
Everything.
And now, what would you like to see?
I'm ready for the next generation of telescope that can see gravitational waves and neutrinos.
Wow.
That is not electromagnetic.
Not electromagnetic.
Yeah,
that would be fantastic.
I know.
Look at that.
Yeah.
Hey, great question, John Meyer. Way to go. All right, this is Tuomas Limata. Hey, it's Tuomas from Oulu, Finland. Long-time lurker and first-time Patreoner.
Long-time lurker?
Lurker, yeah. So he's been watching forever, but he decided
you lurk. You just look over the shoulder.
Now he pulled the trigger, and now he's welcome aboard, my friend. He says, I have a small question that I've been pondering for a very long time. Is time permanent? Thank you. Wow.
I don't know. I mentioned John Archibald Wheeler a moment ago. He's famous for uttering the following sentence. Matter tells space how to curve. Space tells matter how to move.
Yeah.
And that motion is defined to make time look simple.
I love that. That's so great. Motion is defined to make time
look simple. That's right.
Simple.
That's right.
Yeah.
So is time.
So without that, who knows?
Yeah, I mean, I want to believe that your whole timeline is just there, and you're occupying this point in the present.
On the arrow.
That's correct.
Right.
That's correct. I want to think that, and I can sort of do it because I can lay out what's going to happen. That's what a schedule is. What's your schedule? You're
right.
I'm going to be here on Thursday, and there on Friday, and there on Saturday, and that's your future history. I don't know how you would live outside of a timeline.
Right. Yeah. Yeah.
Because where there is no time reckoning, then nothing moves.
Exactly.
Because then you can measure time by that. Otherwise.
Right. Otherwise, yeah. So that'd be kind of cool, though. I mean, no, it wouldn't be. I hate that idea.
To be outside of time?
That'd be outside of time. I hate the idea. However, that's what many people think eternity in the afterlife is that it's in a dimension that exists outside of time. And that's why it's eternity, because time does not exist, you know.
Right. I see.
Yeah.
Okay, that's the reasoning given.
That's the reason given, you know. So you know. Anyway, that's very cool, man. What a great thing to think about.
And by the way, if that's the case, if you're outside of time, then that's the realm of divinity, the realm of spiritual, these sorts of things. I just don't know how a material object could be.
Could it actually be there?
Correct.
Right. No, yeah, that's the whole idea. History allows us to remember our future. So.
Nice.
Yeah. Anyway, Gavin Bamber says this. Hello from North Vancouver. Please visit and please tell me, how much does the universe weigh?
In fact, I'm going to be in Vancouver giving a public talk. May 4th.
How much does the universe weigh?
So you can do that on the back of an envelope.
On the back of an envelope.
We know the mass of the sun. We know the mass of all the planets. A fraction that of the sun.
Right.
We can practically ignore them because it's just in the round-off error.
Exactly.
Then we know how many stars there are in the galaxy.
Okay.
Then we know how many galaxies there are in the universe.
Okay.
Then we know, because we know where the edge of the observable universe is.
Right. Exactly.
We know these numbers.
Okay.
All you have to do is multiply it up.
Right.
Okay. So the sun is 2 times 10 to the 33 grams times, let's say 100 billion stars in the galaxy. So 2 times 10 to the 33 times 10 to the 11th. That's 100 billion. So that's 2 times 10 to the 43rd grams times possibly a trillion galaxies. That's
Right.
To the 12th power. So that's
Fuck ton.
that is the biggest unit of measure there is.
That's right.
It's the vulgar metric system.
Yeah, that's where I got it from. That's why I said it.
I think I had it at a Facebook post, but then I kind of hid it.
Yeah.
But it's out there.
I know. I just remember it from that we.
And when I did that, someone wrote in and said, "This is beneath you."
Yeah, of course.
This is.
Listen.
So that's how you measure the mass.
That's how you measure the mass.
You just multiply it all
we
up.
got the numbers. And
Sorry.
ahead.
I left out.
Go ahead.
Okay. There's 6 times as much gravity in the universe as is what is created by that mass that I just calculated.
Right.
So if that extra gravity comes from matter, then we legitimately are calling it dark matter. So you take whatever number you multiplied up, multiply by 6. And we can do that without going out there with a scale.
Right. Yeah.
There are ways to do this.
Yeah.
Didn't we have an explainer? Was it an explainer or question where we weighed a truck?
Yes. Yeah, we did that. Mile from Macedonia. She says, "Hey, Chuck. Hey, Neil. Mile from Macedonia, Balkan, Europe, world. Japanese astrophysicists have identified a strong gamma ray glow near the Milky Way's center, matching predictions for annihilating dark matter particles, WIMPs." Okay.
Weakly interacting massive particles. They're called WIMPs.
WIMPs. Could you explain how these particles are different from regular matter?
No.
Great.
The hunt for dark matter.
Right.
It's you know who was doing that was Katie Freeze.
Right.
We've had her as guest.
Yes.
You go dig up Katie Freeze.
Yeah. Watch that. That's actually a really fascinating episode that we had.
Yeah, Freeze,
Yeah.
Freese.
Yes.
She's an expert on dark matter detection. She's a theorist.
She's a theorist.
So she would think about what particle would interact with the dark matter particle for that to happen. Right. Now, I'd be surprised if dark matter interacted with such ferocity that it would be giving us gamma rays.
Right.
That's a little bit mysterious to me.
Right.
Because it's we would see that everywhere.
Right, exactly.
You'd think.
Yeah, exactly.
You can't take this one example in our own Milky Way and say, see? When you have a trillion other galaxies.
Right.
That should be a common phenomenon.
It should show up someplace.
Our sample size is so large, you can see even rare phenomenon every night.
Boom, that's awesome.
Yes.
I love that. All right.
A quick reference to medicine. If I have a new a pill, a new cure for something, and it's medicine that you take, it's not safe for, this is an old saying in the field, it's not safe for anyone until everyone has tested it.
Exactly.
Think about that.
No.
You can test on 1,000 people, but if you have a condition that's 1 in a million, it's not likely that you were in that data set.
You weren't in that sample.
You're not in that sample,
exactly.
right?
Yeah.
So ideally, you would test on everyone.
Right.
They know exactly for whom it works and who it doesn't.
Yeah.
That's not realistic.
It isn't realistic. And
whereas the universe is big enough so that extremely rare things happen all the time.
All right, let's go with Larry McGuire. He says, "Hey, Dr. Tyson, Lord Nice. Larry from Caledon, British Columbia, just down the road from the Dominion Astrophysical Observatory."
I use software that they wrote.
Oh, really?
Well, there was a important colleague of mine from that observatory who wrote data reduction software.
All right.
And it was the primary software I used for my thesis, which is sitting right there, that big old fat book down there.
That one right there.
Yeah, yeah.
So he says, "I'm curious about your tools to keep looking up. What was your first telescope? And do you still have a telescope? And what type is it?"
My first encounter with the night sky was this dome of the Hayden Planetarium.
Oh, that's so cool.
Because I grew up in the Bronx.
Right.
There's no night sky to New Yorkers. We had no relationship.
Right.
And so that was my first night sky.
Okay.
Then a friend of mine,
my
best friend growing up,
right,
he was smarter than me in like many countable ways.
Okay.
Right? He taught me chess. He taught me poker. He taught me gambling. So, in fact, I'll give his name. His name is Philip Branford.
Branford.
And when I was on Celebrity Jeopardy, I pointed him out in the audience.
Oh, really?
He came to the show. Came to the show. I pointed him out, and I say, he first got me to watch Jeopardy.
He first got me to watch Jeopardy, and first dude to give me drugs. What was your first telescope?
Okay, so he had a pair of binoculars.
Oh, cool.
And so I looked through the binoculars, and I never knew, we weren't wealthy enough to have like binoculars just laying around.
Yeah.
That's a different. So he invited me to look up with them, and I saw the moon. And the moon wasn't just bigger.
Yeah.
It was better.
Yeah.
It was, oh my gosh.
Right.
And you don't want to look at a full moon because that sucks.
Yeah.
You want to look like a half moon.
blown out.
Yeah. Any photographer knows you don't directly illuminate something.
Right.
There are no shadows. There's no depth. You wait for there to be shadows. Any other phase, ideally half moon, which is officially called the first quarter or last quarter, first or third quarter moons. So you have longest shadows visible. I'm looking at it with the binoculars. It was like, whoa, this is like a whole other thing.
Nice.
Oh my God, I felt like I was there.
Nice.
Yeah. So that was like, tipped me off that stuff was going on up there that the human eye does not notice.
Right.
Then when I'm 11, we moved to Lexington, Massachusetts.
Okay.
We spent just a year there. My father had an academic appointment.
Okay.
And for just 1 year. In the Kennedy School of Government.
All right.
I'm a city kid and we're living in a private house. Like, what's up with that?
Right.
You want me to do what with this shovel? You want me to do what with this rake?
Right.
Oh, isn't the snow pretty?
Right.
And then they hand me a shovel.
Of course.
Right. It's like, what?
Yeah.
Okay. And then it's autumn and the leaves are on the ground. What?
Yeah.
The grass gets long. Okay. What? Mow? What? We just stayed, it was someone else's private home for a year.
Right.
That's what it was.
Yeah.
And they were on sabbatical or something. Anyway, my interest in the universe was stoked because I learned that Harvard had a Center for Astrophysics.
Interesting.
Whole department of it was like, whoa, that's like really cool. And so my parents saw this and they took me there for one of their open house nights. They had telescopes.
Wow.
I rented there. And it was like, I died and went to heaven. And I'm 11 years old.
Wow.
Okay. For my birthday in October that year when I turned 12, they bought me my first telescope. It was a 2.4-inch refracting telescope. That telescope I rapidly outgrew. But I mean, I saw the rings of Saturn, the weather bands on Jupiter, Jupiter's moons, nebulae, the Andromeda Galaxy, the sunspots. I had special filters for that. And then, like 12, and my parents just let me out there observe the sun. Trusted that I knew what the hell I was doing.
Well, no kid walks out with a telescope to go get in trouble.
In retrospect, they would never concern that I did not know what I was doing.
Right.
And then when it did snow. This is New England, right? So there's a lot of snow there. Yeah. I want to take the telescope out back, and winter nights are long,
right?
Anywhere they're long, and the air is crisp.
Yeah.
There's much less humidity,
right?
And so the really good some of the best observing is in very cold nights. So I dug a path into the middle of our back. We had a backyard and a little circle, and that was my little observatory circle. And I would take the telescope out there. And I had several eyepieces, and that's what I did.
That's very cool.
Okay,
man.
So within a year, I outgrew the telescope.
Okay.
We sold it to a friend, we're acquaintance, and then I would then buy my own telescope the next year.
Gotcha.
When I was 13, no, maybe a year and a half later, I would buy my own telescope with money I earned by walking dogs, and that was a 6-inch Newtonian optics reflecting telescope.
Well, okay.
It's 6-inch telescope.
Nice.
That telescope I took to Africa to view a total solar eclipse when I was 14. That telescope has since been gifted to a museum of science in Kentucky who decided to make an exhibit of famous people's first telescopes.
Interesting.
They have my telescope.
They have your telescope.
Yeah, it's like on permanent loan.
That's
there.
great.
I haven't visited there. I don't know if it's on display or anything.
Right.
They got my telescope.
That's cool,
yeah.
man.
And I also took it to the Mojave Desert where I was in astronomy, lived nocturnally in an astronomy camp.
Very nice.
Talk about geeking out.
Yeah, man.
Who else is going to be there but like crazy other
geeks. That's it. That's fun.
Yeah, there were girl geeks and boy geeks, and we were all there. And since then, I went a long period without a telescope when I went to college, and I said, "Time, I got to get back in the game here." Much later, when I had some cash, then I bought a very high quality optical telescope, and since then I have 2 digital telescopes. Yeah, which takes some of the fun out. You go back in to your warm living room, and you just guide it with your iPad. So at the time, I was a member of the Amateur Astronomers Club, which had monthly meetings here at the American Museum of Natural History, under the shadow of the Hayden Planetarium. So I go way back in this.
Nice.
That's
you go.
what it is.
Well,
those are my telescopes.
Very nice.
And in this office, I have a 2.4-inch refracting telescope, which is not my original, but it's exactly the same size. Okay. And in the hallway of the astrophysics department, there's a 6-inch Newtonian reflecting telescope, which is exactly the size of my telescope. But they were selling them in the shop 50 years ago. Wow. And this one was the display model, and we just kept it. And now that the shop is all blended with the other shops. Very nice. And so those are my 2 No, you were the first no one in the department knows this. Right. That I had that telescope there and this telescope there, that same optics. And so when I see them, I feel a little nostalgic. A little nostalgic. Yeah, except for when I was on the roof with my telescope. Right. And then neighbors call the cops. Well, yeah, because, there's some children's books that tell my story growing up. Okay. And one of them retells that story of me on the roof. On the roof? And they show the cops showing up. But then the cops show up and I say, "Have you ever seen Saturn through a telescope before?" Right. And then they're enchanted. They're on. But up until that moment, it's actually quite tense. Of course. But they don't know what I'm telling them to look at. And And that children's book, which showed the cop, was banned in Pennsylvania. Oh, no. Yeah. For what? Because it was showing a police officer in a bad light? Yes. Oh, do you remember there was a period of book banning? Right. That wanted to protect the image. Yeah. And so, and I tracked it, and it was only on the ban list for about 6 months, 6 to 8 months.
This is Sanad from Chicago, Illinois. With all the talk about us living in a simulation, when we look out into the cosmos, or even here on Earth, what are some of the phenomena we've observed that feels like features and feels less like features and more like bugs in the system? I love this question. Ooh. What a great question. It's like, okay, forget whether or not we're living in a simulation. Okay. Let's assume that we are. And then let's figure out the glitches in the Matrix.
Yep. And in the Matrix, there's a scene where they're entering the building. Right. And because they're in the real world in that moment, in their real bodies. Correct. I think so. Is that right? Or
no, they're still in the Matrix.
They're still in the Matrix. And Neo sees a cat. Right. A black cat. And then
he sees it again.
And
he goes, whoa, deja vu.
And Trinity says, what happened? It was just something weird. Don't worry about it. No, tell me what happened. I saw a cat twice. Was it exactly the same cat? Yeah. Did exactly the same thing? Yeah. Then that she knew it was a glitch.
So it was like, that was the glitch in the Matrix. And that meant that they were made and the agents knew where they were.
Yes. Right. Yes. In fact, that was the answer to a clue in a New York Times crossword puzzle a few weeks ago.
What?
Yep. So how much is the universe like the Truman Show? If you didn't see the Truman Show, they created this world for him, raised him in this world, and he had no knowledge or understanding of the outside of this world. And everyone in his world, his friends, his teachers, they were all actors.
Right.
Okay?
He was the only one that wasn't in on it.
And he goes out on a boat to the horizon, and then he gets to the edge, and it's a painted horizon.
Yep.
Oh my gosh.
Yeah.
Your world collapses.
Right there.
Right there and then. The question is there anything when we got up close and it just wasn't real? Right. Or was it fake?
Right.
Okay, that has never happened. But what does it take? It just takes the programmer to be just way smarter than you.
Right.
Okay? How much smarter are you than a dog? So I grew up with a poodle. Poodle's a smart-ass
pretty
dog.
smart, yeah.
I didn't know until I met other dogs. And I said, what's wrong with your dumb ass?
Yeah, a lot of dogs are dumb. I grew up with a German Shepherd, and they're pretty smart too.
Where was I? Oh, we're talking about, are we in a matrix?
How smart are you than a dog?
Yes.
How much smarter are you than a dog?
You could devise things that the dog would never figure out.
Right.
Because you can go 1,000 steps ahead of the dog, and the dog would have no clue.
Right.
So it just takes a really smart alien to program the universe. And so the idea that we can outsmart someone who's way, way smarter than us, I think is unrealistic.
Right.
But there are other things you can look for. For example, if you've ever programmed a computer, there's a place where you put up the parameters with the speed of light. You put in that because you might need that later.
Right.
What is the value of pi? You'll need that later. What is the range of values certain changing parameters can have in your program? Okay? So, for example, if you have people who age, we'll say they can be as young as 0 and old as, let's say, 120.
Right.
You can't say infinity because that's not real.
Right.
Okay? So you put in something. Now watch. Suppose we find out that no one ever lives past 120. People do, we improve health. We keep improving it. People going like gangbusters, and then they hit 120 and die.
Right.
That's not normal.
Exactly.
There's something wrong. That's a glitch. That means we found the limits of the programmer's range of values that they had presumed for us.
Right. Exactly.
That would be a way to determine that. If no one ever lived to 121, yet a bunch of people died at 120, something's wrong.
Exactly.
Now, the cosmic astrophysical version of that, we have cosmic rays.
Okay.
These are high energy particles that come from across the galaxy and across the universe.
Yes.
Very high energy.
Yes.
We can plot how many particles have have different energies. There's like a tail off of their energies. That tells you how energetic the things are in the universe.
Okay.
You can ask, suppose, these are really high energy, high. Suppose there's a cutoff.
Okay.
How do you get a cutoff? Maybe that's the limit that the programmer put in.
Highest value that was put in.
That was put in because they didn't think we would get to that high.
Is that gamma rays?
They would have the energy of gamma rays.
The energy of a gamma ray.
Right. So that's what I think we would need to look for.
Wow.
Otherwise, everything's going wrong just fine. And another thing, we're putting our bias on it. If you dig into the Earth, why would the programmer have to create the whole Earth if you're only digging into one part of it? So why not create the Earth you're digging into as you dig into it?
Of course. That makes sense.
Right.
It's like the old...
Otherwise, you're wasting computing power.
All right. Let's go to Steve Hale. And Steve says, hey, Dr. Tyson, Lord Nice, I am a retired family physician, worked mostly in public health, and a recent Patreon subscriber. Well, thank you for your service.
Yes. Service and support.
Yeah. My question is to Lord Nice. What? Uh-oh. Does he recall in childhood being required to write his last name first, then comma, then first name, therefore Nice Chuck? Yeah. And did he have any feeling or reaction to this? Maybe, why are we demanding Nice Chuck? I will become a comedian and poke fun at them and create laughter. That's not exactly how it went at all. And no, the only problem with being Chuck Nice is very hard to be a dick when I want to be.
Oh.
Yeah. The moment I'm a dick, people are just like, I knew it. Yeah, you're not nice.
You're not nice, yeah.
Or Louis Ferranda, who was the general manager of Caroline's on Broadway, used to call me
Caroline's Comedy Club.
Caroline's Comedy. Used to call me Chuck Mean.
Yeah, but when you did do Nice Chuck, did what thoughts went through your head?
Nothing, because I don't really know if I'm nice to this day. I mean, I think I'm compassionate, but I'm not sure if I'm nice.
You know, nice didn't always mean what it means today.
What's that?
Nice meant honed with precision. So if you had a nice knife, it meant it was sharpened
to
and could perform its task.
Get out.
Yeah, and then nice became a desirable feature of things that were nice, and then it just turned out
into be a nondescript word that we have slap on everything.
Right. This has lost its precision.
That's very cool.
Yeah.
I did not. Nice. Honed with precision.
I think I'm right there.
I'm going to look it up. Here we go.
What do you have?
Dainty and luxurious.
That's interesting.
Delicate as a distraction.
Okay, none of those are what I'm
modern,
saying.
polite,
Yeah.
Amelioration. None of those are good. Precise. Precision. Before finally becoming a term of pleasant kind approval. So the precision, which is
worked its way into
worked
that.
its way to being like, oh, I approve of that. It's so precise.
Yes,
now,
yes, there it is.
So now,
all as one
since
package.
I approve of it, now just the approval part was what we use now,
Okay.
which means,
It was nice.
right. This is Valalov. Tommy from Stockholm says,
Stockholm, Sweden.
Sweden.
Oh, by the way, the Nobel Peace Prize is given in a different city from all the other Nobel Prizes.
Get out.
Yeah.
Why? Just to make that distinction?
I once knew, I don't remember.
Okay.
Yeah, so all the main ones are given in, the quote, regular ones are given in Stockholm.
Stockholm.
And then the Nobel Peace Prize, there's some other city, I forgot which.
Okay.
Okay, go on.
What is the last video game you have played, Dr. Tyson, and what's your favorite game ever?
Wow. Okay, so I was never into violent video games. We had to harm
Other people or other things.
or other things. And I didn't even like Pac-Man because you had to like eat
Right, the other little creatures.
creatures.
Right.
And I thought, not that I had some deep philosophical objection to it.
Yeah.
It was just not entertaining to me.
Okay.
But you know what was entertaining to me?
What?
Tetris.
Oh, of course. It's a puzzle game.
Oh, yeah. Tetris was good.
All right.
And that probably, by modern standards, doesn't even count as a video game, right? It's a video distraction.
It did at one point, no longer.
Yeah. So I'm not the video game guy.
Yeah.
I'm not that guy.
Yeah. I've never played video games. So.
Really?
Yeah. I had friends who would play and I would watch and I just didn't.
Yeah. So I don't have a rich answer to that question.
All right, here we go. This is Michael Stoerzer, who says, hey, could these fully formed galaxies seen by the JWST that seem to be too early in the Big Bang timeline, in fact be fully formed galaxies that is in an adjacent universe that we can see due to this overlapping of universes? By the way, you guys crack me up. Go ahead, yeah.
I'm going to not rule that out.
Yeah, really?
But we don't have other evidence of overlapping universes.
Right.
And we've looked.
Right.
We've actually looked for this. In the cosmic microwave background is a very detailed map of everything the universe was doing when it was 380,000 years old. If another universe went bump in the night against us, we would see some kind of imprint in that background. And people have looked. They've looked to see if the universe doubles back on itself.
Right.
Because maybe you look this way, but something behind you is showing up in view.
Exactly.
Okay, so it wouldn't even have to be another universe.
Right.
Just
It could be the same universe that you're seeing as it coming around.
Coming around.
Right.
And so there's a way to do this statistically. You grab a piece of that pattern because it's all around you, and then you map it in all different orientations onto every other possible place that could be mapped. And we don't see any evidence of the meddling of other universes within our own. So I think we just have to go back to our own, how do you make a galaxy drawing board? All right, because the Big Bang is very secure in all the ways that we recognize that it's telling us what's
the
really
evidence of everything that we believe about it is
strong. And varied. So whereas we built the James Webb Space Telescope to see galaxies being born. That's the whole point of it. So the fact that it found something that, well, we don't know who ordered that. Right. It's doing what we asked it.
And can you talk very quickly, because I know that there are people who get confused because the timeline is the same. The galaxy is born. So how are you seeing it being born? Can you talk about what happens with light?
How is it we can see?
How is it that we can see back in time with light? What happens?
We see the universe not as it is, but as it once was, according to the light travel time from those destinations. I see you not as you are, but as you once were 3 billionths of a second ago.
I have changed so much since then.
Relative to human life expectancy, I don't have to worry about that.
Right.
But on a time scale of the universe, the time delay is long compared with the lifetime of stars and galaxies and other phenomena that unfold. So,
And what specifically about the wavelength of light?
no, it's not wavelength, it's just speed.
Speed of light.
If the speed of light were infinite, we would not see anything in the past. And there'd be no such thing as cosmology. We have no knowledge of the formation of the universe.
And why do we have different lights? Like, why do we have X-ray, infrared?
Oh, there's just bands of light, but it all goes at the speed of light. We can use any one of them.
Okay.
We're good. It'll tell us different things that were happening at that time because different phenomena give off different amounts of each of those kinds of light. Like the cosmic background, that's microwave.
That's microwave.
Yeah, we have we didn't know that until we had a microwave telescope.
The microwave, cosmic background radiation.
Exactly. Galileo didn't have a microwave telescope. He ain't thinking cosmology. All right. By the way, Galileo was the first person to attempt to measure the speed of light. He put his servant or whoever on a mountaintop with a lantern with a shade, you know, a shutter, and he went on another mountaintop, and they would time it, and you know what he said at the end? I'm paraphrasing, but went something like, light, if not infinitely fast, is faster than anything we can figure out by this method.
That's very cool.
Yeah.
Wow, that's very cool.
Yeah, but he knew enough to even ask that question. I
mean, what a great, wow. What a mind. All right, speed round. John Haverlack says, greetings, star nerds. My name is John Haverlack, signaling.
Thanks for the compliment.
Yes. Consider the meaning and context. He says, Hotel California, the Eagles, 1977, black hole. Consider the meaning and context. Approaching the event horizon. Up ahead in the distance, I saw a shimmering light. My head grew heavy and my sight grew dim. Interior observer. Any time of the year, you can find it here. Her mind is a Tiffany twisted holographic information. We are all just prisoners here of our own device, mirrors in the ceiling. Singularity, we stab it with our steel knives, but we just can't kill the beast. You can check out anytime, but you can never leave. Is this a cosmological comparison or a casual coincidence? Thank you. I mean, damn.
There was a period of time between, and I've thought deeply about this, between like 1970 and a half and 1973.
Okay. All right.
In that, when was Hotel California written?
I think he says 77.
That late?
I think so.
Oh, wow. Okay.
He says here 77.
Okay. I have no reason to doubt that. But in that period of time, rock groups wrote lyrics that made no freaking sense. But if you got high or were otherwise drug-induced, they were being deep.
So deep.
And so the fact that sentences and words rhymed but otherwise made no sense was used as evidence that it made sense in a deeper
state of consciousness.
State of consciousness.
Right. An altered state of consciousness. You're absolutely right.
Okay. Yeah. And so, and I'm allowing this to be art for art's sake.
Right. Alejandro Guardado. See? He says, what is the color just between violet and ultraviolet and red and infrared? I know it's a part of the light spectrum, but at what point do we stop seeing the color? Thank you for making the world a better place.
Well, thank you for thinking that. You look at the cones of our retina,
right,
which have three pigment sensors. Red, green,
RGB.
and blue. It's RGB. It's why we know anything about RGB.
Exactly.
We're mimicking our retina.
Right.
And they have sensitivity curves. So right in the middle, they're most sensitive, middle wavelength. And as you go off to each side, they become less and less sensitive. As you go off this red side, there's a point where you stop seeing what's there.
Right.
But there's still something there, as discovered by William Herschel. And he called it light unfit for vision. And its thermometer there went higher than any other color. He said, the sun is, I can't see it, but clearly there's some action there. We call that infrared, below red. You ask what color it is no color because you can't see it. Right on the border of the red pigment of your cones, you don't see a damn thing.
Wow.
You can feel it. Your skin can detect it. Your retina cannot.
Right. So you feel it as heat, but you can't see it.
Can't see it.
And even when you think you can see it, you're not seeing it.
Correct. In fact, infrared lamps,
Right.
you're seeing the part of the infrared lamp that's giving you red light.
That's right.
But that's not the
That's not
infrared
the
that it's
infrared.
going. Right. If you bring infrared cameras in, it'll be way brighter
Exactly.
in the infrared than it would be in the red.
Yep. Okay. Very cool. That's the answer. That's a great question.
So I enjoyed that.
That's always
Those
fun.
are good questions. So what you got for us?
So I do have the science question
Sure.
because this has been bugging me for a while. It's about a couple of slightly related concepts about which I've heard you speak a couple of times. The first being that the fabric of space-time might be woven by microscopic wormholes.
Yeah. I'm still losing sleep over that, but go on.
And then the other one is how we might create our own artificial wormhole and how it requires like negative gravity substance or process.
That's it.
My question is like if both of those prove true, it seems to me like space-time's natural state is to always be expanding, because if wormholes are always pulling space-time apart and space-time is made of wormholes, it seems like the nominal state is for it to always be expanding, which sounds a lot like dark energy to me. Am I misunderstanding any connection
All right,
there?
so you are perfectly understanding the situation.
Absolutely.
So here's a little bit of the backstory. So we see the universe is expanding, and is accelerating in its expansion, implicating dark energy, predicted to exist as a thing in Einstein's general theory of relativity, which he published in 1915. Einstein looked at this term in his equation and it says, this is a negative gravity term. It can't be real. It's probably just zero. So let's ignore it.
Right.
Okay, how could there be a negative gravity? That we haven't seen any, we don't have any evidence of it, yet it came out of his equations. It is possible for equations to have solutions that don't correspond with reality. Okay, I'll give an example. Let's say I'm on a cliff and I toss a ball to you, not a high cliff, but so I toss a ball and it makes an arc and you catch it down at the bottom of the hill. Okay, there's an equation that describes that arc. There's an equation. I can know with high precision using Newton's law of gravity, Newton's laws of motion, using a little bit of mathematics, that this will take the shape of a parabola, okay? And I solve it, and I know exactly where you need to stand to catch that ball. Wait a minute, a parabola is a quadratic equation. Quadratic equation has a square term in it. If you have a square term, then the solution is the root of that term. Then I only found one of the solutions. Every equation that is in a square has two solutions to it. Where is the other solution? Well, you just discard it because it's irrelevant. But it does mean something. Oh my gosh, you know what it is? That's where you would have to stand if I were not on a cliff and I extended the path of that ball backwards. If you were standing on your same elevation below the cliff, but if the cliff were not there. So so the math captured that, even though it was not a real thing in the universe I was working in. Okay, did that make any sense at all? Did you follow that?
That's because you would input like a negative value, and a negative value squared becomes a positive. Right?
Correct. And so the negative place on this grid is behind me, down on a platform that doesn't exist because I'm on a cliff. But that would be the second solution to that equation, which I discard because it doesn't apply to me throwing the ball to you. Okay? All I'm saying is that the mathematics of physical phenomena can, on occasion, give you a result that's not physical to what matters.
Okay.
So it's called the cosmological constant, requires negative gravity. Einstein says probably nothing. Let's not worry about it. So while I was in graduate school, we always had to toss a bone to it. We do a cosmological calculation. What are you assuming for the cosmological calculation? We're assuming it's negative. We're assuming it's zero. Right. Okay? Until it was discovered that it's real and it has value. Okay, getting back to your question. Where does this come from? Oh my gosh. Well, quantum physics says that virtual particles are popping in and out of existence. That could put some kind of pressure in the vacuum of space, later interpreted as mini wormholes through through entangled particles, but this is the same idea. If you calculate how much pressure these particles would create in the vacuum of space using all known laws of quantum physics, you get a pressure, just like you were suggesting. You get an answer. The problem is, it's the wrong answer. It is off by more than 100 orders of magnitude. It is the biggest mismatch between an observation and a calculation ever. And so we're still scratching our heads over this. So the answer is, we hoped it would be this phenomenon you're describing as the cause of dark energy, but we cannot square the circle. We cannot reconcile what quantum physics predicts and what we measure. So watch that space.
Gotcha.
Interesting.
Cool. Well, thank you very much for your time, guys.
All right.
And I really appreciate what you do for us.
Okay, excellent. Thanks for that.
Great
that
question,
support.
Brad Lester.
And stay safe out there.
Definitely. Yeah.
Oh, yeah, absolutely.
All right.
Listen, we're with you, man.
Okay.
You know,
Thank you. Appreciate
right.
it.
Dennis Schrader.
Okay, so what you have?
So, gentlemen, first off, I've been watching for about a year on YouTube. I just started back in September as a Patreon supporter. I'm going to see you in May when you come out here to Seattle. By the way, go Hawks.
Okay, Seahawks, yeah.
Go Hawks.
You guys, I'm a lawyer by trade, but you guys have inspired me to return to my original love. What I started off for my freshman year was in science and engineering. I'm going to go back to school and study physics again. So,
Whoa.
thank you.
And you blame me for that? Okay, I'll take the blame.
I thank you for that. I thank you for that. No.
Oh, and one other thing. Seattle
Yes, sir.
is my deepest fan base in the world. You know this. So when I
I
go
see
to
a lot of this on the comment section. Yeah.
Yeah. So when I go to Seattle, it sells out in like an hour.
Wow.
And so the theater said, put in another show. So anytime I go to Seattle, I'm giving 2 shows. And they're different shows. They say, I'll give a different show.
That's great.
Right, because I give them a list of like 15 topics I can speak on, and they pick. So they don't want me to give the same show. It's a different show. So you can go twice.
Wow.
Yeah, they're trying to maximize, anyhow. So thank you all for just who and what you are as a community. The university is there. It's helped set some of the mood of curiosity that pervades you all. So thank you.
Thank you. So I've written out a question regarding black holes and time dilation. You and others have said that as an object approaches the event horizon of a black hole, time appears to stop for them from the perspective of an outside observer. But time moves normally for the person crossing the event horizon. And if looking outward, that person would see the rest of the universe's time fast forward, basically see the entire future history of the universe, as you've put it.
Yes.
But from my perspective, that person just kind of stops. So if the person crossing the black hole, just because they've pressed the fast forward button, doesn't mean the rest of us don't still have to watch the rest of the movie at regular speed, right?
Correct.
So far, so good.
Wouldn't that mean then that nothing has actually crossed the event horizon of a black hole because the universe still exists? And how do we sort that out with the fact that we know we've seen things like black holes merge and we've seen the result of that merger?
That's brilliant. So I had that same question and I could not answer it based on my foundations of physics and cosmology. So we had Jan 11 in the chair.
That's right.
And I asked her that question.
That's right.
Because I couldn't answer it. And by the way, there was a book published in the 1970s by New York Times science journalist Walter Sullivan. Back then, journalists wrote a lot of the science tracts, not scientists, because it was not a thing scientists did much.
Were like, we're too busy doing science.
That's right.
We don't have time to write articles for you for your enjoyment.
He wrote a book titled Frozen Star, which was about black holes and not crossing the event horizon. So what Jana said, which this is the first I'd learned of this, as you near the event horizon, you are no longer a separate thing from the black hole itself. And what happens is the black hole's event horizon ends up wrapping around you, merging with your event horizon. But I don't know why you would have an event horizon. But there's some merging of the geometry that takes place at the surface so that you're not stuck there forever from the point of view of those looking in. You will actually get absorbed and you will see that happen. And so that's a Jan 11 thing. And I'm going to have to ask you to go dig that up in our archives. Just find anything with John 11 in it, and they're all good. But we're pretty explicit about who the guests are and who the experts are. So in our archives on our website. But so I'm waving my hands with that answer, but that's the answer. But you're otherwise thinking exactly the right way. That if this must be true, then this other thing must be true, and if it's not, how come it's not?
Yeah, and the other thing, I don't know if maybe the way I think of it is right or wrong, but it's always both are happening simultaneously, although they are separate one from the other. So it's based on the observer. So as the observer looking out, you're seeing all this go by, but you're just looking out.
Everybody's got their own
Everybody's
little
just
world.
got their own little world, and these
Mm-hmm.
little worlds exist simultaneously, and that that's kind of like the way I have to think about it.
But what's the title of that movie? Everything, Everywhere, All at Once.
Everything, everywhere, all at once. Yeah, that's kind of how it goes down. Yeah.
All right, so thanks for. Sorry, I couldn't give you a deeper, more nuanced reply, but that is an answer that we did recover from our archives.
My question is about Star Trek. I'm filming this. This is January 2026, whenever people are watching, and I'm filming this from Minnesota. Right now, there is a lot of conflict between people who live here and authorities in the government. And Star Trek has this idyllic future where they've solved those problems, where there's conflict like crazy in Star Trek, but it's not humanity fighting against itself, especially not people against their own government, different governments, struggling for money, struggling for inalienable rights, human rights. They've solved those things. So my question for you, Neil, is have you thought about this? What might be required for humanity to reach a future like that?
I love that. That's a beautiful, timely, insightful question. And I can address it even if I can't fully answer it for you. I'll get 80% of the way there. So, space exploration in general, if we turn the solar system into our backyard, there are unlimited resources there. So, if the world has access to the unlimited resources, then wars over access to limited resources would become a thing of the past. That doesn't get rid of all wars, but it gets rid of a category of war that has reared its ugly head throughout the history of civilization. So there's value to that. Now let's get to the Star Trek model. My read of Star Trek, and I would need the Geek-in-Chief's blessing on this analysis. My read is the main thing that stopped wars was the replicator. Okay? So it's related to limited access to resources. It's related to that, but it has an even bigger solution to it. So I have an orange and Chuck wants the orange. I say, no, it's mine. If you're nice to me, I'll split it in half, but then we each only get a half an orange. I put this in the replicator. It makes an exact duplicate of that orange, and then we both have oranges. The idea that you don't want other people coming into your country has foundations in the idea that we have resource and opportunities that they don't, and they're going to come take it from us, and then we'll have less. And wherever they're coming from, they don't have these opportunities. So I don't think it was some higher evolution of I don't think it was a higher moral evolution that is represented in those Star Trek storylines. I think it's the simple fact that nowhere in the world are you without resources, because the replicator provides it for you, period. And so you don't have to cross borders to gain access. You don't have to fight your neighbor. You don't have to do any of that. And so what it means is now you have just regular old evil people, just people,
people, you don't have an excuse. You're just evil.
You're just evil. You're just evil. And so, so the United Federation of Planets is now unified, and they're fighting evil forces elsewhere in the universe. So I think it's the replicator. And does that violate some laws of physics? Not really. You need a source of energy to turn the energy into matter and exactly duplicate the atomic and molecular form of what it is you're duplicating. So can that happen? Not in the foreseeable future that I can imagine, but that would certainly end wars over those reasons. I think there would still be tribal wars. People will still want to harm one another. You know, Chuck and I can talk all day about the slave trade and man's inhumanity to man and the lynchings in the South. We could talk about that. However, if you take a step back and you look at the slaughter that went on in the First and Second World Wars, which was basically white Christians killing other white Christians, it's pretty clear that the person doesn't have to be dark-skinned on a gender spectrum or any other reason that people have otherwise invoked to commit harm. You don't have to be that because they would find other reasons to do it anyway. All right? And so that is disturbing to me, at least. That's in our genes.
Yeah. There's a definite part of our evolution that has placed us in a position where territorialism, violence, these things are part of our lizard or monkey brain.
No, monkeys are not that evil.
Yeah. Well, there is one monkey that we very much resemble, even though we are apes, and that is the baboon.
No, baboon's an ape.
Yeah. Oh, I'm sorry. Yeah,
I'm pretty sure baboon's an ape.
We're the great apes. I'm sorry. The baboon is a lesser ape. So, but baboons are awful. And sometimes they present as if they're incapable of cooperation.
Okay.
They will form a bond and then immediately backbite, which is where we get that term, by the way, backbiting.
Oh, okay. I didn't know that.
They literally bite each other on the back.
Okay.
But I think that education is one of the things that elevates us beyond. It gives us the opportunity to go beyond what we might be.
I think
in a
the
natural
Nazis
state.
in Nazi Germany were fully educated.
No, I don't mean that kind of education.
Okay.
Okay. So there's something about a indoctrination when
We have a susceptibility.
yes, we have a susceptibility to indoctrination. And
You know what else we're susceptible to? Why is it that we need hardly any proof to believe a lie, but we need all the proof in the world
to believe the truth?
to believe the truth?
Yeah.
That's scary.
It is scary.
Yeah.
So, but what I'm saying is, you put all those things together, that it takes a great deal of maintenance from a very like young age all
Maintenance,
the way
that's the
through.
word.
We need
Yeah.
maintenance.
Yeah, yeah.
And as our psyches require maintenance, and I think if we do that on an individual family level, that we help. Believe it or not, the numbers are not as bad as we think they are. We tend to think that there are more people in the world who are racist and xenophobic and tribalist than there are people who are like bonobos looking to cooperate and love one another. And I think the numbers are very even, and there may be slightly more on the side that we would call good. You know, even though I don't believe in the...
Maybe without that, we wouldn't survive as a species at all.
we definitely
We
would.
have to edge it out.
Our greatest superpower as Homo sapiens is our ability to come together, cooperate, and achieve things in groups. That is our greatest ability. If you look at that and we cultivate that and we maintenance that and we drown out the other voices, then the susceptibility
will go away.
will lessen.
Yeah,
And that's what I think really we need to do.
All right.
Good to see you. I had a question actually following up on Jan 11. One of my favorite episodes you guys did was last year when she came on and you talked about Einstein's different, the crumbs from Einstein. And Dr. Tyson, you made a comment about you can develop like mathematical equations that don't have a basis in our reality. And I'm just wondering if you could kind of expand on how that works, because I have a very basic understanding of math, and that's all.
Oh, okay. Yeah, this is an important thing. And Chuck, maybe we should do an explainer on this at some point. Okay. So let's think of mathematics as something that was out. You know, people like debating, is it invented or discovered in the universe? And I don't join those debates because that's become semantic. And why have a debate over words that are describing something that has such high precision as mathematics itself?
Right.
Why use...
The truth is, it don't make a difference.
Don't make a difference. Exactly.
Whether it's invented or discovered makes no difference. It
To the
works
math.
better than anything.
Correct. So,
Makes that a difference.
so mathematics is precisely logical and defined and effective. Okay. Put a pin in that. Now we look around the universe and I see phenomena that repeat. And I see others, and I ask myself, is there a kind of math that I could attach to what I see so that I can manipulate the math and in a way manipulate the universe itself?
Ooh, okay.
Ooh, okay.
Yeah.
So, as I said earlier to a question, if I now understand gravity and I want to toss a ball to you, using Newton's laws, I derive an equation that tells me exactly where that ball is at all times on its arc.
Right.
That's pretty powerful.
It is. It's a very precise language.
In fact, I'm not just describing what I'm looking at.
Right.
I'm predicting where it will be.
Yeah.
Okay. So that's math matched to the physics. All right. Put a pin in that. We first put a pin in the math. Now I have some physics to apply the math to. All right. Wait a minute. Suppose my idea of the universe is flawed. Well, if I take math and attach it to that idea, the math is perfect every time. But who's to say that my idea of the universe is properly represented by the math I'm attaching to it? So Einstein comes up with a general theory of relativity, which talks about the curvature of space and time.
Okay. Yes.
He doesn't know enough math to do that. So he pulls in some topologists and some geometry people, and they help him find the math of curved space, curved geometries. It's called non-Euclidean geometry. Non-Euclidean means space that's not flat. Most geometry you learn in school, it's Euclidean geometry, whether or not they tell you that. It's just flat.
Right.
Parallel lines meet at infinity, whatever that's supposed to mean. Okay. Triangles, that's Euclidean geometry. Non-Euclidean geometry, we curve the space-time, now still do math on that curved surface. That was a fully developed branch of mathematics. Einstein says, I have curved space-time. Let me borrow some of that. He borrows it, slaps it in. Oh my gosh, it's working for him. It has the right mathematical tools to attach to his physics to make predictions, to make calculations. He gathers a lot of mass into one place.
Uh-oh.
The curvature becomes severe.
Yeah.
And all of a sudden, in one of his equations, he's got to divide by zero. Okay.
Uh-oh.
So you may remember from your middle school math or whatever, you can't divide by zero.
Right.
It doesn't work. Okay. The result goes to infinity if you divide by zero. So what that tells us is you can't blame the math for that because the math was doing just fine until he tried to make the math everything that his theory was. So something else has to change in the physics so that the math doesn't give you that singularity at the center of a black hole or at the Big Bang itself. That's where you're dividing by zero. Some have joked to say it's where God is dividing by zero. Well, no, God would probably have an understanding of the universe where that's not even necessary.
Right.
Right? That's the crutch that comes about when your idea of the universe is not completely all there.
Right. Yes.
So that's a case where the mathematical model of the universe got you pretty far, but there was a point where it broke down. And so you have to modify the physical model, get the math that would apply to that, and then continue on your way. So, in summary, when we describe physics with math, it is our best invocation of math as a representation of my model of the universe. And if it is perfect, then I can forever manipulate the math. And in so doing, I'd be manipulating the universe, taking my model to places that I didn't even know it could go.
Right.
So the math assures you that steps you take with that model are logically accurate for every next step you take. You can't just make stuff up. Once you go there,
I just didn't understand.
Yeah. So I mean, it's a fascinating fact that the math works at all.
Yeah.
Okay. There was a physicist, Eugene Wigner. I met him once. He was like, I'm coming up, and he's like on his way out. He was like 85. Eugene Wigner, I think he was a German, a mathematician, physicist, who commented on the unreasonable effectiveness of mathematics in science. It's just out there, and you just slap it into your idea, provided you did that right. You just calculate away. And quantum physics is doing that for us.
Yeah.
All the math of quantum physics, we take the math, manipulate it another way, we make a prediction, oh my gosh, it comes out to be true. That's what tells us that maybe the universe is mathematically constructed.
Okay.
And Max Tegmark, my favorite name of anybody's name.
It's a good name.
This has been a Max Tegmark production. Physicist at MIT.
Yeah.
He's been on StarTalk.
That's right.
He wrote a book called The Mathematical Universe, where he is exploring everything that you know, see, think, and do. If you can make a mathematical model of it, then he takes the next leap and says, that means you can program it.
All right.
Oh.
Which is kind of why people say we could live in a simulation.
There it is.
For that reason.
If it's all mathematically programmable,
and programmable, why not? Why couldn't it be a simulation?
You just got to get the right math to go to the right theory of the universe.
Yeah.
And then you're all good.
Okay.
Plenty of theories work with a little bit of math, and they say, let's make another prediction from the math, and that prediction never came true. So they just threw away the model.
That doesn't work.
It just doesn't work. Exactly.
Here's my question. You often mention photons travel at the speed of light at all times.
Yep.
Working as an optics engineer and dealing with TIRF microscopes, I wonder how evanescent waves during total internal reflection, TIR, is thought of from a particle physics perspective. Are the photons moving at the speed of light but somehow without propagating? Or the photons don't exist at all? But then, what is interacting with the sample on my microscope? Thank you. I love your work. P.S. Chuck, you surely deserve an honorary PhD by now, my brother. Oh, look at that.
My brother.
My brother.
Optics
Yeah.
is a huge field
Yes.
that does very important work on a lot of frontiers.
Okay.
Optics is, what do you do with electromagnetic waves?
Mm-hmm.
Do you bend them? Do you reflect them? Do you trap them? Do you heat? What do you do with them?
Mm-hmm.
An entire branch of physics and engineering addresses those questions. So I don't know how specific the example is that he's giving and how that would lend itself to my explanation. Okay. So what I will otherwise say is the speed of light is not just a good idea.
It's not just a good idea. It's the law.
It's the law. Thank you. That's a dated reference to 55 miles an hour speed limit when we wimped out and said we're not going to go fast anymore.
Right.
So that doesn't mean light always travels at that speed.
Exactly.
It means it will never travel faster than that speed.
Right, because you can slow it down.
So let's see how you do that. Okay, it turns out you sort of can slow it down.
Right. I got you. So the medium itself can slow the travel.
Yes.
The
However,
medium.
But the way it slows it down is fascinating.
Interesting.
Okay.
Okay.
So I'm a beam of light. Then you hit the air, or you hit a piece of glass or a piece of water. This is for visible light going through what we would say are transparent object.
Right.
Okay. If you're transparent, it means the light stays coherent as it goes through,
Okay.
so that the waveform maintains its structure. If it does not maintain its structure, light can still get through, but we would not call it transparent.
Right. Yes.
You know the word we have for that?
Translucent?
Translucent.
Yes.
And lucent means light in Latin.
Latin, yeah.
Loose is light. Loose. So the light comes up to the boundary. Some light will get reflected.
Yes.
And optics people know and understand that. Okay? That happened no matter, you can't do anything about that. You can try to minimize it by having what are called these coatings that will delete any attempt for the light to reflect back. Right?
Yeah.
And you know, it's fun the way they do that. You have a coating that's half the wavelength of the light that you're using. So then the light goes through, and by the time it wants to reflect back, the light that's coming in is out of phase with it.
Oh, so it creates a disruption.
And it flattens the light.
Look at that.
Coated lens prevents the reflections off of surfaces.
Interesting.
Okay? And cameras, especially zoom lenses and other big industrial cameras, they have many, many lenses in them.
Yes, they do.
You can't have light reflecting off of shiny surfaces at every time there's a surface.
Yeah.
Okay?
You just end up with a blob at the end.
Just a blob at the end, and all the light was scattered everywhere. You got nothing.
Right.
And when I say it reflects, because light will reflect off of practically any surface, whether or not it's a mirror.
Yeah.
That's what I'm saying. Okay.
As a matter of fact, in photography, they have something called a bounce board, and it's just a stark white. I forget the color of white.
So it diffuses the light that it comes back to you.
And that's all
Otherwise,
it
a
does.
flash can be very harsh.
Right, exactly. So you bounce it off of there, and you get the light without the harshness.
Without the harshness. So now you took care of that. Now the light enters the medium. Between molecules,
Okay.
light is moving at the speed of light.
Gotcha.
But it hits a molecule, I got to deal with the molecule. I got to go in and come out.
Damn it.
Yeah. Tourists are just in the way.
They are in
in
the
ways
way.
that New Yorkers are not.
That's right.
And I figured I analyzed that.
Go ahead.
I figured out why.
Why?
May I say?
Please go ahead.
I'll try to relate it to light going through a medium.
Okay.
Okay. Here's why. New Yorkers anticipate each other's trajectories because we've done this with each other before.
It's a dance that we know. Yes.
It's a dance we know. Whereas a tourist, they might step left unannounced.
Right.
Nobody told you to step left.
Yeah.
Because I'm about to pass you on the left.
Yeah, who does that?
Who does that?
Who does that?
But a tourist who's just ambling on
Looking up.
All
right.
ambling.
Right.
And so you can't predict what their next move is, but for other New Yorkers, you can.
It's true.
Not only that, there are people who are, I've walked perpendicular to people, they're on the sidewalk and I'm crossing the street. You time it.
That's
so
right.
that you
know exactly when.
Exactly.
No, it's a dance.
It's a
You
dance.
got to live here to know the dance.
Whereas the tourists will stop.
Right.
Well, now they just messed up my timing.
Exactly.
Okay, they'll look, they'll say, excuse me, pardon me.
Right.
And you get people, I'm trying to get in the subway, okay? And a train just lets out. There are people, tourists will wait for everyone to clear from the stair. So the combination of getting through the molecule plus the speed of light between molecules, on average, slows down the propagation of light through the medium.
Look at that.
This is called the index of refraction.
Woo.
It's a beautiful mathematical construct.
I love it.
The index of refraction. Yeah.
Ooh.
Yeah. So.
Oh, I love it.
And I'll tell you how it works.
Go ahead.
The index of refraction, you can use that in a formula to tell you how much the light will bend coming in or out of that medium. That's how you make a lens at all. Okay. But the index of refraction, if you take the speed of light and divide by the index of refraction,
Go ahead.
that's the speed of light in that medium. Ain't that something?
That is really cool.
Okay, so let's do the math. The index of refraction of diamond is 2.4. What is 1 divided by 2.4? 1 is like the speed of light. Divide by 2.4. What's the number? It's
0.4 something.
Exactly. It's
0.4
about
something.
0.4.
Yeah.
So light in diamond is going 40% as fast as it goes in a vacuum.
That's awesome.
Isn't it?
Oh, I love it so
Yeah,
much.
yeah. And so diamond is one of the hardest natural substances known.
Exactly.
It's hard for light to get through as well.
Yes, it is, yeah.
And even though it's transparent.
Right.
And before we get all emotional about light trying to get through the medium, visible light can't get through most mediums. Like a brick wall,
Right.
the light ain't going to do it all.
Yes.
But other wavelengths of light are transparent in these other substances, as you know. So your cell phone works in here because the walls are transparent to microwaves.
Right.
Microwaves come right on through.
No problem.
No problem.
They don't travel well through plaster, though.
What are you talking about?
Because my house, the walls are plaster. My house was built in 1898.
I think there might be something else in your walls.
Oh, you know what? You're right.
You might
it's
have
a metal lathe.
metal grid.
Lathe plus, so here's what it is. It's plaster, then it's wood, then it's lathe, then it's metal.
I bet there's a metal mesh.
It's a mesh.
To hold up the plaster.
To hold up the plaster.
So you're in a Faraday cave, my son.
Oh, my God.
Faraday cage.
That's what it is.
That's right. If you're surrounded by a metallic anything,
yeah.
okay, then the electrons in the metal will conspire to prevent electromagnetic energy from entering.
That's wow! Look at that. Okay.
Yeah, back then they would put up the mesh.
Yeah, you put the mesh,
and
you put the plaster.
It would hold the plaster up because all of the little the grid of the metal.
Yeah.
So if you have multiple internal reflections, that's the light just going back and forth. Oh, by the way, check this out. Check this out. Okay, ready?
What?
Okay. So if I have two media with different indices of refraction. Okay. So I have light coming up from one. It crosses the border and it bends. Anytime you go between two media, the path of light bends. It will bend. Okay?
Right.
That's why sunset happened 5 minutes ago.
Right.
Because the light bent going from the vacuum of space to our atmosphere, and it gave us an extra 5 minutes of sunlight because it refracted around your horizon.
Nice.
Okay. So it will bend.
Okay.
Now watch this. It comes up and it bends.
Right. Yes.
Suppose I take the angle of the light and make it steeper, like this. Then that will keep this come further and further down. There's an angle at which the light never enters the next medium.
Oh.
Because this bend now takes it backwards into the medium itself. And it's called total internal reflection.
Oh, wow.
It's still in the other medium.
Right.
Bam. Now it's total internal reflection.
That's pretty cool, man.
It's very cool.
I love that.
And you can know exactly what that angle is,
right?
How to do that. And so if you have an optical system where the light is just bouncing back and forth, it is within the parameters of, or you can have just a reflective surface as well.
Right.
Just a mirror would do that. Mirror. Right. But anyhow, what you do inside your medium is your business. And what that then does to a beam of light. But yeah.
Interesting.
There it is. That's all I can do to illuminate. See what I did there? To illuminate that question. There may be other places to go in the physics of optics that I would not have known to touch.
Very cool, man. All right, this is Big G. He says, hey there, Lord Nice, Dr. Tyson, Big G here from California with a question for each of you. Are there any cosmic mysteries that you are most looking forward to knowing their resolutions, but sadly may not be resolved in our lifetimes? Bonus points if you can name mysteries that we are so close to resolving, but it's probably just beyond our reach.
Okay, you go first.
See, mine is the easiest because I just want to know what exactly is causing the acceleration, the expansion of the universe.
Like everybody else wants to know that.
Because that's everybody else. But the reason is because I believe that it's a pressure from outside of our universe that bleeds through. That's what I think it is. And I just...
You think there's a puppet master?
No, well... I'm not going to call it a puppet master. I think there's a bleeding. Because if we were to find that out, now we have to explore the leak. And that means we're looking at a whole nother universe. And to me, that's fascinating.
That's interesting.
Yeah.
You have to then explore the leak.
You got to explore the leak now.
Okay.
So
I can't top that. I don't think we're going to know for sure if there's life in the universe in my lifetime.
Whoa.
Intelligent life in the universe.
Well, then you win the bonus points because that is something we are very, very close to, but it's very possible we may not find in our lifetime.
Yeah, I don't think in my lifetime we
Yeah.
will know that. What we will know in our lifetime is if there's any life at all
Outside.
in our own solar system.
In our own solar
Okay,
system.
because we're looking at Europa.
Right.
We did a whole episode.
Enceladus.
We went to JPL,
Right.
Jet Propulsion Labs.
That's right.
NASA in Pasadena.
That's right.
Talked to the Europa Clipper people.
That's right.
Talking about what are they going to do, how are they going to measure it, what's beneath the ice. So we will know whether or not
Yeah.
there has ever been or is currently life in our solar system other than on Earth.
Yes.
I think that will happen. But it would be sad if there is no life other than life on Earth. You know what has been said?
Mm-hmm.
How profound it would be if we discovered intelligent life in the universe, but how more profound it would be if we discovered that we're alone.
Listen, the second one is far scarier.
It's a little scarier,
than the
isn't
first.
it? No, it would feed many religious thinking that the whole universe is just for us. Some branches of Christianity, and perhaps other religions as well, require that life on Earth be the sole object of God's creation.
Okay, I'm just going to say it, and please don't judge me here. I'm being logical, and I'm thinking like God. I don't need to do all this, okay? I don't need to do...
You're God. You're God
I'm
speaking.
God right now. I don't need to do all this to show you that you're the only thing necessary and good and my central and crowning creation. As a matter of fact, all I really need is the sun and the earth, because that's the energy system that makes all of this happen.
Yeah, nothing else matters.
Nothing else matters. So if the sun, like a hydrogen atom, had just the earth going around it, then I would say there is a God and he made this just for us. But when you look at the vastness of the universe and the trillions of galaxies, all of which containing stars, billions and billions of stars in each galaxy, to a place where we can't even fathom the number of celestial bodies that are out there.
Inefficient manufacturer
and that's it.
of worlds.
Right. It doesn't make any sense. So either there's a lot more of us out there, not meaning us, but life all over the place.
This was Giordano Bruno's argument.
Who was that?
A 16th century monk.
No, really?
In Italy.
Yeah.
Yeah. He had just read Copernicus' book, De Revolutionibus, which puts the sun back in the... I say back because the Greeks knew this, but it got lost in the Dark Ages. But the sun back in the middle of the known universe.
Okay.
He, religious man,
Okay.
God-fearing man, said, if the sun is in the middle and not Earth, that means Earth is a planet going around the sun like Jupiter and Mercury and Mars and Venus. If the sun has planets and we're life on a planet, maybe these stars in the night sky are just like our
us.
sun. And if they are, maybe they have planets.
Wow.
And if they have planets, maybe they have
Life.
life.
Right.
Heretical. Because that meant Earth was not the object of God's creation.
There you go.
So they put him on trial, sentenced him to death,
Oh my God.
burned him upside down,
Oh, Lord.
naked in the Campo di Fiore, the piazza in Rome.
Right.
And I think that's in Rome, not Florence. And they drove a stake into his mouth
To shut his ass up.
so that even in the afterlife, he would not preach such heresies. You know what one of his last words were? He had a few good last words. My favorite among them was, "Your God is too small."
Yes. Ooh. Way to go out.
Way to go out.
Way to go out, man. Your God is too small.
Too small. Your God of just earth and the sun?
Yes. Yes.
Yeah. So anyhow.
Oh my God. Okay. First of all, I'm got to read up on this guy. Bruno is his name, huh?
Giordano Bruno.
Giordano
Cool name,
Bruno.
too.
So check this out. some people know my background, but one of my last words before I left my other life, my religious life, was over this whole idea of homosexuality. I never understood it. I still don't understand it, like why people have a problem with it and why would God have a problem with it. I couldn't get around it as I'm studying to become, a minister. So one of my last...
You know what someone told me? A Jewish person told me. Leviticus are just suggestions.
Kind of.
Because if they were important enough, they would have been a commandment.
It would have been commandments. Right. No, seriously. Yeah. The Levitical law. And by the way, it's a Levitical law for the priests. Okay, anyway. I said... A God that needs me to fight this battle for him is not a God I want to serve.
Ooh.
If God needs me to fight this battle...
homosexuality.
Yeah, right. What? If that's the battle that I got to fight...
Interesting.
I got to be worried about two dudes doing it. I can't serve that. I got to be out. Anyway, so I love this Bruno dude, and I'm going to...
Yeah, check him out.
I'm going to check him out.
All right.
Awesome.
Oh, by the way, there's a memorial to him in the square. He's there. He's got his monk robe on, and he's very solemn there.
Giordano Bruno.
Yeah.
Oh, I can't wait.
I think it was 1601, something like that. Yeah.
That's amazing. Wow, what a great story. I love it. Okay, this is Keith Koenigsberg. Yes.
With
Keith,
a K.
With a K.
Yeah.
Keith says, hello, Team StarTalk. This is Keith here, writing from New York, big city of dreams. Here's a question I've been wrestling.
It's like the first one we've gotten from New York.
It's so true. We don't get a lot of New York people.
We're right here in my office in the Hayden Planetarium, and we're getting from Syria,
right?
From
Pakistan, from all kinds of Chile.
Right. That's cool.
He says this: LIGO has used light waves to detect the shrinking and expanding of space caused by passing gravitational waves. But wouldn't the waves be in and out of the material of space? If space expands, don't your light waves stretch along with it? And any other measuring rod, as Einstein would say, and cancel out the change. So
yes.
Okay. Explain to me
what the hell
he's really asking. Because I'm confused.
What he's saying is we have a laser that bounces back and forth.
Right.
Okay. We measure the trip of that laser with very high precision.
Very high precision.
What he's asking is, if a gravitational wave washes over the measuring device, how's the measuring device going to know if everything about it moves with it?
I got you. Okay.
So if I'm measuring your height, how tall are you?
I'm 5'10".
I'll give you 5. I'm gonna give you 5'9". That's it. Okay. So you're 5'9", and I have a 5'9" tape measure, and you look at it, it says 5'9", right? Okay. Then we stretch both you and the tape measure. You're still 5'9".
True.
Unless you have some other way to measure what just happened. So you're absolutely right. If I stretch you and the tape measure, you're still 5'9".
Right. But we're talking about something washing over the measurement system.
That's fine. So now watch. It's because of that fact that LIGO, Laser Interferometer Gravitational Wave Observatory, has 2 lasers at right angles to each other.
Oh.
So if one of them stretched, moving that way, it's not stretching the other one.
Way.
And it's those 2 path lengths that we compare with each other.
Gotcha.
That's how we know. If a gravitational wave washed over us. So we got smart people designing this.
That, first of all, is a brilliant question. And secondly, those people, they deserve the money.
What money?
Whatever money we gave them to make LIGO.
The funding.
Yeah. Whatever the funding was, they
National
deserved
Science Foundation.
They deserve that, because that, first of all, what a simple little answer to what could be, altered results.
Right.
Interesting. I love it.
So 1915,
right?
Albert Einstein puts forth the general theory of relativity.
Okay.
A year later, he uses the general theory of relativity to predict the existence of gravitational waves.
Right.
But he doesn't think we'll ever detect them.
Of course.
Because the energy level's so low. And how
would you detect
them? It's 1916, for goodness sake. Okay. That same year, he publishes a paper on the stimulated emission of radiation, which is the foundation for the laser.
Right. 100
years later, in 2016, or was it 2015? 99 or 100 years later,
Okay.
we discover gravitational waves using lasers.
Damn. Bro, Einstein was gangster.
Gangster.
He was gangster.
Gangster.
Okay?
Gangster.
That's like a chicken laying an egg so you can discover an egg.
Normally, you would digest it into something more profound.
I know, and poetic.
But that was worse in all counts.
It probably is, yeah. Go ahead. That's Einstein. He was gangster.
Gangster.
Oh, yeah, that's dope.
All right.
Okay, that's really... Scott Jarbo says this. Hello, Dynamic Duo. My name is Scott Jarbo from Seattle, Washington. And you mentioned, I believe recently, that we cannot gather data from sending a probe into a black hole, as we would have no way to transmit any data collected because it could not escape the gravity of the black hole. Okay? So my question is, understanding we can't at this time, if we quantum entangled the instrumentation of the probe with a twin probe that was kept external, could we not record that data that way? And in fact, in general, would that not be a feasible mechanism for interstellar communication in faster than light speed? The state of each should instantaneously mirror. Is that correct? Quantum entangled.
I'm not a black hole entangled expert.
Okay.
So it feels plausible that you should be able to entangle particles even though you lose one of them into the black hole.
Right.
It feels like you should be able to do that.
They should know what the other particle is doing, even though it's inside of a black hole.
Should. But, and so someone interacts with the particle that just went into the black hole, which then triggers the measurement of the one outside the black
particle
hole.
Outside of the black hole.
And that way you knew something happened in the black hole.
Right.
I don't see why that wouldn't be possible. I don't know what to say. I don't see why not.
Okay.
No. But they want to talk about faster than light communication. Right. The problem is your thing has the information already built into it.
Right.
You can't, after the fact, change that information.
Now that we know.
So this normally communication happens where, turn left instead of right.
Right.
All right. And if it's already built in, I can't do that.
Right.
And so there's still some jury that's out on how we will fully exploit quantum entanglement as a communication mechanism going forward. And from what I have read, it's less favorable than you want to believe it is. Okay. For these reasons.
All right.
Okay.
Right. All right. This is James Peterson. Hello to my personal astrophysicist and personal science comedian. My name is James Peterson from Lacey, Washington. Here are my scenarios and related questions. Two manned spacecraft are approaching each other at a constant rate within a huge cosmic void. Neither one is accelerating or decelerating. There are no other visible or detectable objects within this cosmic void, just the blackness of the vacuum of space. Neither of them knows if they are moving or stationary. They only know that they are approaching each other at roughly 20% the speed of light. What would be the reference point for each of them to determine their individual velocities, assuming that they could compare rates of time on their clocks as they pass? Could the relative speed of their clocks be used to determine their individual velocities, and individual velocities relative to what? Everything is relative, you know?
What he's not getting right in the question, the simple point, is each of them does not know if they're moving. As far as they're concerned, they're stationary.
Right.
So he's saying, well, they approach each other. I don't know that. As far as I'm concerned, I am still in a void, and I see this other craft coming towards me.
Right.
There it is. That's the only thing that matters. That's it.
Right.
That's it. And so I will measure how fast he's moving.
Right.
There'll be time dilation relative to me as a function of how fast it's going. It's not more complicated than that.
That's it.
We don't have to do a double calculation.
Nothing.
Or anything. And we will each measure exactly the same thing about each other.
Right. because it's relative to the observer.
It's relative to the observer.
And
correct.
so each one of us will see the other ship coming. We will measure that.
And we will think we are not moving
and
at
we're
all.
going to still stay stationary as far as we're concerned.
Correct.
And when the ship goes by, it's like, whoa, did you see that?
Right.
And that's going to be the end of it.
That's the beginning and end of it.
Right. All right. So this is Vexonar, who says, greetings, Dr. Tyson.
What is who?
Vexonar.
Vexonar, okay.
Vexonar, who says, greetings, Dr. Tyson and Lord Nice. What are you putting in your time capsule for the next generation to open?
Oh,
Interesting.
So, I just got to say this, okay? Mm-hmm. And there's a book written on this. I forgot the name of it. Forgive me. And I don't remember the author. Mm-hmm. But there's nothing less interesting to a subsequent generation than an earlier generation's time capsule.
Wow.
And the evidence of this is nobody remembers where any of the time capsules are buried. There's ceremony. There's a mayor speaks, and then as things move on and culture advances and technology advances, no one cares what your sorry ass from 40 years ago thought was modern.
Right.
I was in Flushing Meadow. Near the Unisphere.
Okay.
Tell everybody what the Unisphere is.
It's the thing outside of the old World's Fair Stadium. It's a big giant globe, right?
Yeah. I mean, it's the one that it's what anyone thinks of when they think of the Flushing Park.
Yeah.
Okay. It's Earth. U.S. Steel created this for the World Fair. And there's these 3 rings around it.
Right.
Evocative of John Glenn's 3 orbits around the Earth.
I did not know that.
I'm just saying. So there I am. This is maybe 15 years ago. I'm just sitting on a bench. I forgot why I was there. I don't remember. Forgive me. I don't remember why I was sitting on a bench in Flushing Meadow. Because I don't live in Queens. Usually I'm just driving through Queens.
Okay.
But I'm sitting there, and I look down, and under the brush, I parted from. Here is a time capsule from 1965. It was like a time capsule buried in that spot. No one cared.
And they just put a bench on it.
No one cared.
Nobody gave a damn.
There's no memorial around it, no ceremony, nothing.
Exactly.
We have a time capsule for the Rose Center here. And they asked me, what do I want to put in the time capsule? So I thought about it. I said, okay, I'll tell you what I put in it. I put a Metro card in it. I think I put in an iPod.
Oh, okay.
Okay.
And interesting.
This was modern stuff.
Right.
At the time. We're all excited about it. But who cares?
Right. Because like both of those things are non-existent now.
They're non-existent, and no one wants
and
one.
Nobody wants one.
No one cares about them. No one wants one. We moved on.
Right.
So for me, time capsules, though they mean well, I think are one of the greatest misplaced investment of our attempt to communicate with the future.
Okay. Dr. Tyson, Lord Nice, greetings from Hungary.
Hungary, love it.
Yeah, way to go. In an earlier episode, Dr. Tyson said that mathematically, the horizon of the universe has all the same properties as the event horizon of a black hole. That got me thinking, if our universe would be a black hole, knowing that gravity has no limits on range, could the continuous falling in of matter into our black hole universe explain accelerating expansion of our universe? And if that would be the case, is there any possible way to detect such matter since it would be at the edge of our known universe? Thank you for your work.
That would be true. Good question. That would be true if we were not expanding exponentially.
Right.
Okay, so the fabric of the universe is expanding, and because of that, there's nothing falling in.
Right.
It's taking it with it out to the edges.
Yes.
So, but if we were not that way, and we just had our horizon, an object moving could just kind of cross our horizon and show up. It'll just show up, okay, if it moves in that way. Or you wait enough time, I should say that differently, wait enough time, that horizon washes over the next set of galaxies that are sitting there waiting to be seen by you. Because right now the horizon is 14 billion light years away. Wait a billion years. Then it's 15 billion. That's a whole extra universe that's in your horizon.
Right.
You know the scariest day of them all will be?
What?
You wait another billion years, and there's no new galaxies to reveal themselves. It meant you reach the actual edge of the universe.
Yes. Not just the observable universe, but the edge
of the whole universe itself.
Right.
That's a scary day right there.
That's kind of a cool day, though.
It's kind of cool.
Yeah.
But it also means cosmology will evaporate because at that distance, we're seeing things that are that old getting born. But if there's nothing there, then the galaxies that 1 billion years ago were just born, they're now 1 billion years old.
Right.
In another 1 billion years, they're 2 billion years old. And there's nobody new coming in that's just being born.
Mm-hmm.
Gone is cosmology.
Look at that.
Yeah.
Wow, that is a scary day. All right, this is Bill.
This might be the last question, I think.
Okay, last question. Look, Bill gets the last question. Bill says, "Hi, Dr. Tyson, Lord Nice. This is Bill." And he says, "I need some cheering up considering the state of the earth in a few hundred years, maybe sooner, if he whose name we shall not mention gets his way. From now, when humankind has finally turned Mother Earth against us, which species that exists just now would you imagine will pick up the cloak of dominance that we humans held for a few thousand years? Will they be land-based, sky or sea-based, or even amphibious? What is it about the species that leads you to that conclusion? Or do you see a bright future for us and what that future would look like in the event we are still here in 25?
I have some important replies to that.
Go ahead.
So first, there's a book written, forgive me, I don't remember the author. It's called After Man.
After Man.
Something like that.
Okay.
Okay?
And is that like...
What it does is it renders humans extinct and it looks at other animals to see what would become of them. So
After Man.
And so I looked it over. I didn't read every word, but it's highly illustrated. It's intriguing.
It is.
Okay.
To think about.
Okay. Now,
because who would have bet on us?
Consider, what's the largest animal there ever was?
From what I understand, it is the blue whale.
And it is alive today.
It's alive today.
And what kind of animal is it?
It is a mammal.
Mammal.
Yes.
Okay. Do you know the size of the smallest mammal?
I don't, but I think it's pretty small.
It can fit inside of it like a teacup.
Yeah.
It's like this big.
Yeah.
I think it's a marsupial.
Yeah, it's like a little shrew or
Marsupials
something
are mammals,
like that.
I think.
Marsupials are mammals.
Yeah. It's some little thing.
Yeah.
Okay, this big and the whale. So mammals have the capacity to not only occupy practically any size range, but practically any place on Earth. They can figure out how to live there.
And we are on every place on Earth.
Basically.
We're even
so are bacteria, but in terms of animals,
Yeah.
reptiles, and other cold-blooded creatures, they can't exist in cold climates. Right? Because they would just freeze and die. But we maintain our body temperature no matter where we are. All right. The reason why I'm saying this is this book said, if that's the case, what's limiting the size of rats?
I don't know.
I'm going to tell you. You ready?
Go ahead.
The size of the hole they will run into so that you don't harm them.
Really?
Okay. Just think about that.
Yeah.
Go look in the subway. You see rats?
Yeah.
They'll crawl, and there's a hole they go into.
There always is.
There always is.
No matter what rat you're talking about.
There always is.
Right.
There's a hole.
Yeah.
Okay. If humans aren't here, they don't need the hole.
Oof. Which is why you get some, they're not rats, but they are part of rodentia in certain parts of the world where they're as big as like
a capybara.
Small horse. Like a capybara.
The biggest rodent is right. So rodents, which are one of the most successful branches in the tree of life.
Yeah.
For how many they are and how many species there are. Okay. How many species are there in the branch called Homo?
I don't know. Not one. It's Homo sapiens.
Homo sapiens.
We're the only ones left.
Correct.
Because when you say how many species, I was trying to think
we're
of
the only ones left.
Denisovians.
That makes us
Homo erectus
quite fragile on the tree of life.
Yeah.
Rodents.
So many of them.
So many of them. Okay, so this book foresees that basically rodents take over. And they become huge. Like people-sized. And there's nothing to...
And nothing to stop them.
Nothing to stop them. And it talks about... the aquatic creatures,
right?
What is it? The penguin gets really large or something,
right?
So when you take away a predator, there's no longer a limit on the size of what it is.
Okay.
So Earth after humans, I picture a natural history museum And there's like human skeletons there. So that's the future of Earth. Because Earth and other life forms are going to survive us.
Right.
For sure.
Right. Exactly.
Okay? So, but in terms of hope, here's the hope.
Mm-hmm.
Our boy here is from Scotland.
That's right.
I gave a public talk a few nights ago. Someone asked me what was my favorite song ever.
Really?
And you know what I told them?
What?
Amazing Grace.
Okay.
I think that's the song of the millennium. Amazing Grace.
It's a beautiful song.
It's a beautiful song. And you know how it's most beautifulest?
Okay. No.
In bagpipes.
Okay. I'm not a fan of bagpipes.
You would be if you heard it and play Amazing Grace.
You know.
That's all I'm saying.
Okay.
And bagpipes, that's a Scottish thing.
It really is.
So what I'm saying is, when life and the world gets us down, we should hear chorus of bagpipes performing Amazing Grace. How sweet the sound.
Let's save
the wretch like me. Because we're all wretches and we need saving.
It's true. From each other.
So Scotland may be the savior of us all.
Well, look at that.
All right, we gotta go.
Right?
Oh, man.
That was fun. That was so much fun.
All right, this has been yet another Cosmic Queries. What kind of edition?
This is Cosmic Queries Grab Bag.
Grab Bag with Chuck Nice, of course. Neil deGrasse Tyson here, your personal astrophysicist. Always good to have you, Chuck.
Always a pleasure.
As always, keep looking up.